Hello and welcome to Sleepy Science. I'm so glad you've found your way here. Whether your day has been heavy with noise or light with curiosity, this is your quiet place to rest your mind in the glow of wonder. Tonight, we'll drift slowly through the strangest corners of quantum physics puzzles. So strange, they bend our very idea of reality, from paradoxes, where the past can change depending on what you do in the present, to experiments where the universe itself seems to wait for your decision before becoming real. This journey is both soft and impossible, like a dream that teaches as it calms. Before we begin, I'd love for you to share something in the comments. Tell me where you are listening from, or simply write a few words to let me know you're here. And if you enjoy these gentle explorations, please take a moment to like the video as well. It truly helps more sleepy minds find their way here. Your words and your support keep this small circle of quiet science alive and growing. So now, take a slow breath, let your body sink into comfort, and let's begin our gentle descent into the shimmering world of quantum paradoxes. The Frauchiger-Renner paradox, quantum theory against itself. Imagine a quiet game of sealed envelopes. Two friends sit inside two tiny rooms, each with a table, a lamp, and a notebook, while you and another friend wait outside with your own notebooks. And the rule of the game is simple but strange. No doors are opened until the very end, and everyone must reason carefully about what the others might have seen. This is the spirit of the Frauchiger-Renner paradox, a thought experiment with a big, friendly question tucked inside it. If everyone follows the same quantum rules and thinks clearly, can we end up with a set of "I am sure" statements that cannot all be true together? To start gently, picture a special coin that does not behave like an ordinary coin, but like a quiet chord of music, where heads and tails both softly exist at once, until someone checks, and the first inside friend flips this quantum coin, and depending on what they see, prepares a tiny particle in one of two ways, then passes that particle to the second inside friend, who measures it and writes down a result. And right there, the story already feels normal to the people inside, because each of them has a definite note in their notebook. The strangeness grows only because you and your partner outside keep the doors closed and treat each entire room, person, paper, lamp and all as a single delicate object that can still be described with the quiet chord, meaning you do not pick one inside story yet. You carry both at once in your math, like holding two possible endings so gently that neither one crumples. Now here is the clever knot. The paradox ties inside, friend one says, "Given what I saw when I flipped the special coin, I can be sure friend two will never write a certain outcome." And friend two, after their measurement, says, "Given what I saw, I can be sure the outside observers will never get a certain global result." While you outside, because you kept both inside stories alive as maybes, can calculate that your special outside test sometimes will give exactly that global result the inside friend said was impossible. So if we treat all these personal certainties as if they live in one big book of facts at the same time, we get a contradiction. One line saying, "This cannot happen," and another line saying, "This happens with some chance." It's important to notice that nobody is cheating, nobody is sloppy, and nobody inside sees two answers at once. The C-lash appears only when we try to stitch together what different people are each allowed to be sure about from their own point of view, while also insisting that quantum rules apply to everything, including rooms and people, to make the heart of it kinder. Think of three comfort rules we all like without noticing. First, the universal rule, which says the quantum recipe works for every object, if you are careful enough, not just for electrons but for whole labs. Second, the single-story rule, which says there is one final outcome everyone must agree on when a measurement is done. Third, the past certainty rule, which says if I can be sure of something, and you can be sure of something about me, then we can combine our certainties like dominoes and be sure together. The paradox shows you cannot hug all three rules at once, because holding them all tight is exactly what makes the contradiction. So you must loosen your arms around at least one, and hear different groan. Up interpretations simply choose different loosening tricks, which we can explain in bedtime language without heavy math. One choice keeps the universal rule and the past certainty, but gives up the single story, saying that when a quantum choice happens, the world branches into separate, non-talking files. So each person's certainty is true in its own file and never clashes with another. Another choice keeps the single story and the universal rule, but weakens the past certainty, saying that probabilities and certainties belong to each thinker and can't be chained across minds until information is actually shared. So you cannot just paste "I am sure" onto your page. A third choice keeps the single story and the past certainty, but trims the universal rule, saying large systems don't stay in delicate maybes for long because the wave physically settles. So your outside test that needs a very gentle superposition of a whole room just can't work in nature, and the contradiction never gets off the ground. If this still feels slippery, imagine 3 blankets that cannot cover 4 corners of a bed at the same time. You can tuck 2 corners perfectly, but one corner will always peek out, and which corner peeks out depends on which blanket you pull. What should you carry away as you breathe slowly? First, the paradox doesn't say the theory is broken. It says our favorite trio of everyday assumptions can't all travel together on the same bus. And that is a gift, because it makes us say out loud which ticket we are buying. Second, none of the people in the story are wrong from their seats. Inside and outside are different seats, with different views. And the contradiction only appears when someone tries to mix all the notes into one melody without asking whether those notes were meant to be played together. Third, this puzzle gently trains your mind to respect perspective in science, to ask who knows what and when, before deciding that a fact is global. In real experiments, it is wildly hard to keep a whole room in a delicate, maybe because the world bumps and jiggles everything, like wind that pops soap bubbles. So the paradox lives mostly as a careful map of ideas rather than a daily lab recipe. But its lesson is practical when you use quantum rules to talk about observers who talk about observers. Choose your rules with care. Now let your eyes rest on the soft ending. You do not have to fix the universe tonight. You only have to notice that some of the comfort rules we love belong to different boxes, and that choosing which box to open is part of the adventure of learning, so you can fall asleep peacefully knowing that the universe is not arguing with itself. It is inviting you to ask better questions about how stories, knowledge, and measurements fit together. And tomorrow you can pick up the thread again, a little wiser about which corners you want your blankets to cover. Wigner's friend, when 2 observers disagree on reality. Picture a quiet room with a closed door, a friend inside, and you waiting in the hallway with a notebook. And imagine the whole scene like a bedtime story where nothing jumps or shouts. Because the mystery here is gentle. Your friend measures a tiny particle, writes down what they see, and feels sure of their result. While you, standing outside like a careful librarian, treat the entire room, your friend, the table, the paper, and the particle, as a single delicate thing that can stay fuzzy until you open the door. This is Wigner's friend, a thought experiment that asks a simple but deep question. A child might also ask, if 2 people look at the same situation from different places, and both use the rules of quantum physics correctly, can they disagree about what is real right now, and both still be right? To follow the story, start with the idea of superposition, which is just a calm way of saying that before we check, a quantum object can be in a blend of possibilities, like a quiet chord holding several notes at once. And when someone measures it, the chord settles on one clean note, a definite outcome that your friend can point to and say, I saw this. Inside the room, your friend does exactly that. Perhaps measuring the polarization of a single photon or the spin of an electron, and seeing a firm answer that makes sense. Then they make a record, maybe a pencil mark or a light on a screen. And from their point of view, the fuzziness is over. The particle chose. The story is written, but you outside are doing something daring and very polite at the same time. You do not open the door yet. You treat the sealed room as if it were itself a quantum object, the way a music teacher treats a whole violin as one instrument. And while the door stays closed, There is nothing stopping you from describing the room with a superposition that includes both possibilities for what your friend might have written. A careful mathematical maybe, that keeps both ladders up until you look. The oddness arrives, because both of you are following the same physics, and yet you use different descriptions. Your friend says, "The measurement gave me this result, full stop." While you say, "For me, before I open the door, the whole lab can still interfere like two ripples on a pond." And these lines are not mistakes, they are just two frames on the same film, one close-up and one wide shot, and the film is quantum theory. If we let the story continue, you outside could in principle perform a very gentle global measurement on the sealed room. The kind of check that looks not at what the friend wrote, but at the quiet interference between the two possibilities the room might still hold. And if nothing disturbed the delicate state, your test could reveal a telltale pattern that only exists when multiple stories are still alive together, which is something the friend inside would never predict if they think the result was settled for everyone the moment they saw it. If instead you open the door and read the paper in the ordinary way, the room becomes like any normal object, the interference vanishes, and you and your friend agree on the same single outcome. So there is no fight, just the realization that what counts as a fact in quantum land depends on which questions get asked and when. The heart of Wigner's friend is not to trick you with math, but to help you notice a soft but powerful idea. A fact in quantum physics might be tied to an observer, a bit like a secret you learn in a whisper that is true for you. Yet until someone else hears it in the same way, they are allowed by the rules to tell a different, larger story that still works. And only when you share information in the same frame, when the door opens, do your stories lock together. Different interpretations answer this in different voices, without drowning you in jargon. So think of them as bedtime helpers who tidy the room in different ways. One helper, called Many Worlds, says both outcomes are real in separate branches of the story. So your friend's certainty and your outside interference are not fighting. They simply belong to different branches that never mix. Another helper, called Relational or Agent-Centered Approaches, says a quantum state is like a promise about what one observer expects. So your friend's "I saw this" and your "I still see two possibilities" are both correct in their own circles, and it is a category mistake to paste them together before you talk. A third helper, the objective collapse idea, says the world itself chooses one outcome when things get large enough or noisy enough. So superpositions of big objects like rooms collapse quickly, and the outside interference test becomes impossible in practice. Bringing everyone back to a single shared story as a law of nature. What should you, a curious listener, carry away without getting tired? First, that the math of quantum theory lets us treat OBS, errors and systems with the same calm rules. And when we do, perspective matters. Because what is real for an inside witness and what is real for an outside witness need not match until information is exchanged. Second, that this does not mean anything goes. The predictions for each viewpoint are crisp and testable, and the tension shows up only if we mix statements taken from different frames, as if they were one. Third, that science is not embarrassed by the question. It invites it, because it helps us design better experiments and sharper language for words like measurement, record, and fact. You can visualize the whole thing as two cameras. Filming a play, one camera on the actor who reads a line and writes a note, another camera locked outside on the door and the stage lights, and each camera cuts a different film that is perfectly coherent on its own timeline. And when the door opens, the films match. But before that, you cannot splice their frames without care. For a child, the lesson is gentle and kind. If you and a friend watch a magic trick from two different angles, you may each tell a true story that sounds different. And both stories can be right until you compare notes, and comparing notes is what turns my truth and your truth into our truth in the physical world. In real labs, making a whole room behave like a single fragile quantum object is incredibly hard, like balancing a soap bubble on a feather, because tiny bumps from the environment ruin the interference. Yet the thought experiment is priceless. because it keeps your mind awake to a deep possibility that facts are born when, and where questions are asked, not floating fully formed everywhere at once. As you settle into the quiet end of this tale, notice how the puzzle does not ask you to pick a favorite hero. It simply invites you to be careful with perspective, to be patient about when you decide a story has a single ending, and to feel a small peace in the idea that disagreement between observers is not a failure but a clue, a signpost guiding you toward the moment when the door opens, voices meet, and the many soft maybes of the world fold into the single shared now you can hold in your hands. The delayed choice experiment, changing the past by observing the present. Imagine you are walking through a museum that has a quiet corridor splitting into two identical hallways. And at the very end, there is a curtain that the guide can either keep in place or pull aside at the last moment. And your job is to release one tiny firefly and then wait to see where it shows up. If the curtain stays up, the two hallways remain separate, and you will find the firefly on one side or the other, like a clear either-or choice. But if the guide suddenly pulls the curtain aside, just before the firefly reaches the end, the two paths merge into one stage, and patterns appear that only make sense if the firefly's glow somehow explored both hallways at once, and then the two possibilities blended together. And here is the astonishing part of the delayed choice experiment dreamed up by John Wheeler. We decide whether to keep the curtain or remove it after the firefly has already set off, which feels as if our present choice is deciding what the firefly must have been doing earlier. In real life, the firefly is a single photon, and the museum corridor is a simple interferometer made of glass plates that split a beam into two roots, then either recombine those roots or keep them apart. And the two outcomes are as different as footprints in fresh snow compared to ripples overlapping on a pond. When we keep the roots apart and check for which path, we always see one definite detector click, the kind of record you can circle in a notebook. And when we let the roots recombine, we get bright and dark spots from interference, a telltale signature of a wave that seems to have taken both ways. And because we choose between these two arrangements after the photon has already passed the first splitter, it is tempting to say that we changed the past, yet the karma lesson is sweeter and deeper. In quantum physics, the past in the gap between those devices is not a finished paragraph we can read without asking how the story will be told. It is more like a sentence with two possible endings. And only when we decide which question to ask do we discover what counts as a fact. To make this even more wondrous, Wheeler suggested a cosmic version where a distant quasar shines, and a giant galaxy in the middle acts like a natural splitter, bending light so that two grand roots travel around opposite sides of the galaxy before heading toward Earth. And with clever telescopes, we can either bring those two ancient roots together to look for interference, or we can resolve them separately to learn which side the light took. Our choice happens today, while the light left the quasar billions of years ago, and the data we collect will either whisper both roots together or point to a single path, which sounds like changing long ago. But again, the gentle truth is that we are not sending messages backward in time. We are choosing which kind of question makes sense for that traveler, wave-like blending or particle-like path counting. And nature answers in a way that fits the question we actually ask. This is not a loophole or a trick. It is the heart of complementarity. The idea that some properties live in pairs, where asking clearly about one hides the other, like choosing to listen for a melody or for a single bell tone. Both are music, but they do not arrive at the same moment, for the same note, and the delayed choice adds one more quiet surprise by telling us we do not need to lock the question at the start. We can still pick which story to complete at the end, and the universe will remain consistent. It simply will not let us keep both stories at once. If you are a child hearing this, hold the picture like this. The firefly is brave and small and polite. It agrees to play whichever game you set up at the exit. And before that choice, the state of the game is not secretly decided. It is truly open in the quantum way, which is not vague, but rule-based. It gives interference only when no clues exist. even in principle, about which way the firefly went, and it gives path facts only when the setup allows such clues to exist. So our present action does not flip yesterday. It decides what kind of yesterday we are allowed to describe. Scientists build these devices carefully to avoid bumps from the environment that would spoil the delicate blending. And when the interference appears, it is like a soft signature that says both routes were part of a single possibility. Until the end, and when the which way record appears, it is like a fingerprint that says the routes were kept apart and the firefly left a single file. We can read, both are beautiful, both are true within their frames, and switching frames late is allowed yet never creates a paradox. Because we never see wave patterns and path facts for the same photon in the same run. We only see the answer to the question we chose. The gift you can take to sleep is humility wrapped in curiosity. Reality is not a movie that runs without us and then waits to be watched. It is a conversation where the question shapes the kind of answer that can exist. And the delayed choice reminds you to be patient about naming the past. To notice that clarity arrives when you choose the right kind of light to shine on your puzzle, and to feel a warm calm in knowing that nothing spooky needs to happen, to time for wonder to be real. Sometimes learning how to ask is the part that changes you, and when you finally close your eyes, you can imagine the museum hallway again. The quiet guide, the small glow, and the soft curtain, and you can smile because you now know that choosing when to open it is as much a part of the story as the path behind it. The quantum eraser. Erasing knowledge changes reality. Imagine a kind museum where light is the visitor and you are the guide. And at the entrance, you hand each tiny visitor a secret sticker that could tell you which hallway it chose. Then later, just before the visitors reach the final gallery wall, you decide whether to keep the stickers readable or to wash them away, so no one can tell who walked where. And the surprise is this: when the stickers are readable, the wall shows simple dots with no delicate ripples, just here or there. But when you wash the stickers away, the wall begins to draw soft stripes of light and dark, as if each visitor had quietly explored both hallways at once, and now the two possibilities can braid together into a pattern. This is the feeling of the quantum eraser, told gently so even a child can follow, because the heart of the experiment is not that your memory changes the past. It is that the world's patterns depend on whether which way information exists anywhere in the setup, even as a hidden clue that could be found. And when that clue is erased, the door to interference opens again. Now breathe in the simple picture behind the story. A beam of light meets a device that splits it into two paths, like twin hallways, and a second device can paint a tiny tag on the light that could reveal the path. A tag that might be a polarization twist or a little color code too small for our eyes, but real to the apparatus. And as soon as the tag means the two paths could be told apart, the ripples vanish. Because ripples need matching waves to overlap cleanly, like two singers who must sing the same vowel to blend, and tagged waves refuse to blend. The eraser is just a kind washer that removes or hides the tag, so the waves become indistinguishable again. And then the wall brings back the stripes. Not because we changed yesterday, but because we changed what counts as a sensible question today. Which path or which pattern? And nature is kind enough to answer whichever we ask with a consistent voice, to make the magic a touch richer without making it heavy. Imagine the light comes in twins from a special source. One twin heads to the wall where the pattern might appear. The other twin takes a side trip to a small station where you can keep the path information or erase it. And when you later compare notes, you find something wondrous. If at the station you kept the which way clue, the partner detections on the wall sort into simple dots. If at the station you erased the clue, the same wall detections sort into neat stripes. And if you forget to sort and just look at the wall by itself, you see no stripes at all, because the stripes and anti-stripes from different groups quietly cancel into ordinary dots. So there is no cheating and no message moving faster than light. Just the deep lesson that patterns live in correlations, in how we pair lists and decide which stories belong together. Feel how this is actually friendly and not scary. The experiment teaches that interference is not about a person forgetting something with their brain. It is about whether the physical setup allows the path to be known, even in principle, like a treasure map that may be hidden under a floorboard. If the map exists somewhere, the room behaves one way. If the map is shredded into confetti, so no one can ever piece it together, the room behaves another way, and your hands never reach into the past. You only open or close doors to different ways of seeing what happened to keep it gentle for your mind. Picture 2. Water ripples meeting in a pond. When the ripples share the same rhythm, they add and subtract to form bright and dark rings. When they carry mismatched rhythms, they refuse to form clean rings and everything smears. The which way tag is that mismatch. The eraser restores the shared them, and the wall is just a careful notebook that records the result. Scientists build these devices with polarizers, beam splitters, and detectors that click like tiny drum beats, and they learn to protect the fragile ripples from bumps and noise. Because a stray vibration is like a loud shout in a library, it ruins the quiet blending. And this is why the full quantum eraser usually shows its stripes only after you sort the clicks by what happened to the twin. You need the quiet of good bookkeeping to hear the music that was always there. If you want a child's handle to hold, try this sentence and say it softly so it sticks. The world lets you see waves when no footprints exist, and lets you see footprints when footprints exist. And you cannot have both at the same time for the same traveler. The eraser does not backspace time. It just removes the footprints so waves can sing again. Now ask one more helpful question that turns this from a trick into a tool. What do we learn about knowledge? We learn that in quantum land, a fact is not only a mark on paper, it is also about which marks could exist and be read. Potential knowledge carries weight, and by shaping what can be known, we shape which story the world is allowed to show us. A path story or a pattern story, both honest and both complete in their own frames. Let this settle into your breathing as a life lesson too. Sometimes you look at your day and count steps. This many tasks, this many wins. Other times you step back and you see a pattern, a tide of effort and rest. And just like the wall, your view depends on what you allow yourself to compare. Neither view is wrong. They answer different questions. And so the quantum eraser, with its kind washing of tiny tags, invites you to be careful and curious at the same time, to ask clearly, to record carefully, to sort wisely, and to feel a peaceful confidence that reality is not playing tricks. It is offering two honest games and waiting for you to choose which one you want to play. And when you close your eyes after this story, you can picture the museum again, the two hallways, the quiet washer at the end, the gentle rain of light on the wall, and you can sleep with the warm thought that understanding grows. When we learn to decide not only what we want to know, but also what we are willing to let go. Retrocausality. Can the future affect the past? Pretend you are walking through a maze that has both an entrance and an exit you already chose. And imagine that instead of only the start telling you where to go, the finish quietly pulls on your path so that all your turns line up to reach it. Not by changing the steps you took yesterday, but by making the whole journey fit both ends at once. This is the soft doorway into retrocausality, the idea that in the quantum world what you do later can help decide which earlier possibilities were ever allowed. And we will keep it calm and honest, so even a child can feel it. Think of the world not as a marching parade where drum beats push one by one from past to future, but as a story printed on both the first and last page, where the middle must read in a way that makes sense for the beginning and the ending together. Start with what you know. Regular causes run from earlier to later. Touch hot tea, and you pull back your hand, yet many of the deep equations of physics are time-symmetric, like a movie that looks physically okay played forward or backward. And quantum theory adds a twist by letting us set boundary conditions at both ends of a little experiment. A preparation at the start and a selection at the finish, so that the statistics in the middle reflect both. Like a crossword where clues from the top and bottom shape the same letters. One friendly example uses single photons. You prepare a photon in a gentle way at the source. Then at the end, You only keep the runs where a detector clicks in a certain channel. And when you look at the weak, non-invasive measurements made in between, the patterns seem to know about your later choice. Not because you sent a secret signal backward, but because you saved only the stories that match both the start and the finish. Just as a teacher may grade only the pages turned in, and those pages decide which practice steps were relevant. Retrocausality fans say we can take this filtering seriously as a real picture of nature, where influences come from both directions in time and meet in the present to pick outcomes. While critics prefer to say the future does not push the past, it only filters our bookkeeping. Yet both sides agree on two gentle facts that keep the peace. First, you cannot use these tricks to send a message to yesterday or beat the lottery. The no signaling rules of quantum theory are strict, like a careful librarian who refuses to stamp a book with a date that breaks the catalogue. Second, no paradoxes like the grandfather story appear, because the allowed histories are self-consistent, more like a puzzle that only admits solutions where every piece fits without contradiction. To settle your mind, imagine a coloring book with a castle on page 1 and a sunrise on page last, and the colors you choose later for the sunrise quietly limit which shades of the castle make sense at the start, so that the whole book looks like one painting. But you never see the sunrise reaching back with a magic hand to repaint a page you already colored. You only see that when both pages are fixed, the middle pages had fewer choices. Scientists build gentle versions of these ideas, with what are called pre- and post selections, and with weak measurements that barely touch the system, like listening to a music box through a pillow so you do not spoil the tune, and when the data from the middle seems to lean toward a choice made at the end. It feels like the future is peaking, but the full record still respects ordinary causality once you collect all runs, which is why no one can exploit the effect to break time. Why even talk this way then? Because retrocausal pictures give a local explanation for spooky quantum links that bothered Einstein, saying that two entangled particles need not signal faster than light. They can simply share constraints from both their shared past and their shared future measurement settings. So the surprising correlations arise from a whole timeline handshake rather than a dart flying instantaneously across space. This does not force you to accept retrocausality. It just offers a map with fewer monsters on the edges. The map says reality may be stitched by conditions at both temporal ends, and the present is the seam. Everyday life still has a clear arrow because entropy grows, like a messy room that almost always gets messier. And this thermodynamic arrow makes causes feel one way to human hearts, but down in the tiny quiet of quantum events, where probabilities rule and information is counted carefully, a two-ended description can sometimes be simpler, like drawing a straight line by fixing two pins, and pulling the string taut if you worry about free will. Breathe. Retrocausality does not mean your choice was decided long ago or that tomorrow is dictating your today. It means that when you do choose, the set of histories that were always allowed shrinks to those consistent with your choice. So your decision still matters. It selects the path that was waiting for you like a door that only opens when you knock. If you want a child's test to keep, try this. Can any scheme let me send a birthday message to last week? No, because whenever someone claims that, the math of quantum theory quietly cancels the trick when all outcomes are counted. So what remains is a gentler lesson. Questions asked at the end help define which earlier questions were meaningful, not which facts change, compared with the delayed choice and eraser tales you may have heard. Retrocausality is not about curtains or washing tags, but about seeing the whole play at once. Stage directions written at the opening, and the closing guiding the actors in the middle, without anyone running backward off the stage. So what should you carry into sleep? This soft clarity. The future does not bully the past. It co-authors it by trimming the script to a story that fits both the first line and the last, and you, living in the present, are the reader who turns the page and discovers which version of the middle was always going to make sense with the end you freely chose. Let that thought slow your breathing, because it is both humble and empowering humble in admitting that reality may be bigger than push and pull, empowering in reminding you that choosing a destination can shape the path you walk without erasing the steps behind you. And as your eyes close, imagine the maze again, the entrance you remember, the exit you pick, and the quiet paths between them aligning into a graceful thread. Not because time broke, but because the story you and the universe told together needed every turn to lead home. The page Wootters mechanism. Time emerging from entanglement. What if the whole universe were like a single giant painting that never actually moves? Yet inside that painting you still feel your heart beating, your thoughts unfolding, and morning turning into afternoon because of how parts of the painting point to each other, like tiny arrows that say now and next. And after that, this is the gentle door into the page Wootters idea. A way to think about time not as a great drum outside the world telling everything when to step, but as something that appears from within the world, when one part plays clock for the rest. And the trick that makes it possible has a soft name you already know, entanglement, which is just a perfect kind of matching between two things. Imagine a storybook with two columns on every spread. The left column is a clock column, with a picture of a hand on a dial. The right column is a world column, with a picture of what the playground looks like. And the entire book sits on a shelf all at once. As a finished object, no page slides by on its own. Yet, when you open to any page number, you see a pair that fits. The left shows the clock hand at that number, and the right shows the swings and shadows at exactly the scene that belongs with it. So if you flip the pages in order, you feel a flow, not because the whole book is changing on the shelf, but because the pages are arranged to match in a way that creates the feeling of before and after when you read them. Page and Wootters asked whether the universe could be like this, a single unchanging quilt of correlations, where a small part acts as a cue. Quantum clock and the rest looks like it is evolving when you condition on what the clock shows. And the beautiful answer their math gives is yes. Under the right conditions you can have a global state that is timeless, while the conditional state of the world relative to the clock obeys the usual rule of change you learn about. In quantum physics, as if the right column of the book still follows the familiar melody when you point to a number on the left. To keep it simple, think of two toys inside a box that no one shakes. One toy is a tiny clock that can point to many positions at once. The way quantum things can hold many possibilities before you look. The other toy is a tiny world whose features are coordinated with the clock, and the two toys are entangled so strongly that whenever the clock hand is found at a particular tick, the world toy is found in the matching pose. So the full description of both together can be one big calm object with no outside time. But the moment you use the clock hand to label what you see, the world appears to change in step with that label. This is not a trick to make you dizzy. It is a kind way of noticing that time can be a relationship rather than a background. A story about how one set of readings lines up with another set of readings. And when those lineups are perfectly woven, the experience from inside is of motion and growth, even if the global picture is still. You might ask whether this is only poetry, but people have played with small versions in the lab by using one photon as a clock and another photon as the system, and preparing them in a joint state with the right matching. Then, by reading the clock photon in a sequence of gentle ways, they see the other photon behave as if it is evolving step by step, even though the full two-photon description is orang. Did like our quiet book. The idea also speaks softly to a deep puzzle that appears when we try to blend gravity with quantum rules, because the big equations that describe the universe as a whole can look timeless, like a curtain that refuses to show a ticking clock. So Page Wootters offers a friendly path. Do not search for time outside the curtain. Look for it in the correlations between parts, and let the clock be a piece of the stage rather than a metronome in the wings. There are important caveats that even a child can understand. No clock is perfect. Real clocks get fuzzy and tired, and if the clock toy is too sloppy, its matching to the world toy will be loose, and your feeling of smooth change will blur, which is why better clocks give crisper time, and why the universe might feel more precise when many things act together as a kind of averaged clock. And there is also the practical fact that you must be careful not to disturb the delicate matching while you read it, because a loud poke can spoil the correlations the way a sudden shout can break the harmony in a duet. What you should carry from this is a new way to see something familiar, that your sense of before and after might be born from how things are tied to other things. And if you choose one piece as your clock and ask how the rest looks whenever that piece is here or there, you recover the ordinary rules of change without needing a master timer outside the world, which is a little like discovering that the rhythm you walk to is the rhythm you and your surroundings make together. None of this says time is fake or your memories are illusions. It says that from the inside of the universe, the most useful meaning of time is relational. And this meaning can be powerful enough to restore the dance of cause and effect, even when the biggest description stands still, much the way a map on the wall never moves, but still guides your steps if you decide which road name counts as your now. And there is a gentle life lesson hiding here too, that so much of what feels like flow in your day arises from relationships. The order of your breaths with your thoughts, the pattern of light at your window with the sound of your feet. And by paying attention to these matchings, you can slow the rush without stopping the music. You can sense that change is not a storm crashing in from outside, but a tapestry woven by where you point your inner clock and what you look at next. When you finally rest your eyes, picture again the spread of the book, the clock column on the left and the world column on the right. The page is already complete, and yet inviting to be read. And remember that time, in the page Wootters' view, is the gentle thread you stitch when you let one part tell you how to read another. And that thread is strong enough to hold a universe of moments without any drum beating from beyond the page. Wheeler's paradox: does observation create the universe itself? Suppose the universe is like a silent room full of unlit pixels, and the only way any pixel turns on is when a clear question is asked of it. A gentle yes or no that tells the pixel which color to glow. Not because your mind is magical, but because asking is another word for touching. And touching is how nature decides between the many quiet possibilities it carries. John Wheeler called this a participatory universe, and wrapped it in a riddle that sounds wild, but stays kind if you hold it softly. Does observation help create the very world we observe? Not from nothing like a wizard, but from the menu of what the laws already allow. The way a camera does not invent the scene but chooses which picture becomes the one that lives on film. Begin with a feeling you already know. A photograph only exists as a real picture once the light has reached the sensor and left a mark. Before the click, there are endless frames you could take. After the click, there is a single image the album will remember. And in quantum physics, that click is not just a convenience. It is the event that turns could be into is. A tiny yes or no that becomes part of the world's story. Wheeler stretched this to a cosmic scale, with a question that is as gentle as bedtime: if the universe offers many possible paths for a particle of light crossing the deep. And if we decide today which kind of question to ask about that journey, do we help decide which path becomes the path that is recorded? Not by bullying yesterday, but by selecting which of yesterday's allowed stories is the one that belong in the book we are writing with nature. This is not the same as the hallway and curtain pictures you may have heard before, so keep a new image instead. Imagine a connect the dots drawing where the dots were placed by the rules long ago, and you hold a pencil now. There are many shapes the dots could become, but only when you choose a way to connect them does a dolphin or a mountain come into view. And the drawing you make is then the one that exists for everyone who looks at your page, while the unrealized shapes remain in the land of might, have, been. In Wheeler's language, the it of things we touch and name comes from bits of information gathered by asking nature questions with detectors, cameras, and measurements that leave records in rocks, bones, and bites. And observation is bigger than eyes. It includes any act where a system meets another system, and a fact is stamped into the world, like a raindrop stamping a ripple onto a pond. It is true that this can sound spooky if you imagine thought alone summoning mountains. So let us be careful and kind. Wheeler did not mean that wishing makes atoms. He meant that the concrete facts we count on are concretized when interactions happen. and that the universe grows its remembered story through the building of records, which can be telescope images, fossil layers, or even the whisper of ancient light in the sky. If you want to see why this is profound rather than scary, think of a child's treasure hunt with 2 sets of instruction cards tucked in envelopes. One set draws you around the left side of the garden. The other set leads you around the right. Both sets were printed long before, but you only get one set when you reach the gate and choose a color. And the treasure you actually find is the one that matches the cards you chose. The other cards become irrelevant. Not because they were fake, but because you never played that version. In physics talk, the laws of nature set the menu. Observation picks the dish, and the dish becomes the fact others can taste. Wheeler's paradox asks you to lean into this, without losing your balance. What if the great history of the universe is a tapestry woven by these tiny choices that solidify facts, so that reality is not a finished statue standing without us, but a living mosaic that invites contributions from every interaction that leaves a mark? That does not mean late choices erase early records. It means early regions of the tapestry do not count as part of the final pattern until threads from later regions stitch them in. And once stitched, they are stitched for good. Which is why we cannot send tricks to yesterday or win games by whispering to the past. Another way to feel this without math is to picture a glow-in-the-dark poster that has been painted with an invisible image. The paint was placed by the rules long ago, but the image appears only where you shine your small flashlight today. The beam does not repaint the poster. It releases light from places that were ready to glow. And the path of your beam writes the memory your eyes will keep. People sometimes ask whether this idea is just philosophy, but it has teeth you can chew on gently. Every measurement we make is an act of copying a feature of the world into a stable record, and the world you know is the collection of those records, arranged in a self-consistent chain. The more records, the more classical the world feels. The fewer records, the more the world can keep its options alive. So your role as an observer is not to dream the world into being. It is to participate in choosing which allowed option becomes part of the permanent library. Critics of the boldest version will remind you that stars formed and oceans boiled before any eyes were here. And Wheeler would nod and say, eyes are not the only observers. Interactions act as measurements too. A cooling rock registers rain, a crystal registers a passing electron. The cosmic microwave background registers the early universe. The world is busy stamping its own passport, with or without us. And we are latecomers who learned to read the stamps and add our own. The deep kindness of the idea is that it gives meaning to questions and responsibility to questioners, because in a participatory universe, the queries we pose shape what can be said afterward. And so science becomes a conversation where well-posed questions build reliable bits that compile into the shared it of reality. And this is empowering for a child or a grown-up. You matter not by waving a wand, but by asking clearly, by placing instruments thoughtfully, by letting nature answer in her own steady voice. If you are looking for a single sentence to carry to bed, try this one, and let it slow your breathing. The world is not a movie already burned onto a reel. It is a stage where the rules set the props, and our careful questions invite scenes to be performed and recorded, scene by scene, until the play that could have taken many paths becomes the play that did. And when you finally close your eyes, imagine the unlit pixels again, and your tiny yes or no lighting them one by one. Not to invent a fake picture, but to reveal the one that fits the rules and the questions together, and feel the quiet joy that you are not just watching the universe from a cold seat outside. You are gently helping to write its remembered story by the way you listen, touch, and ask. Quantum decoherence. Why the classical world appears. Imagine you are trying to hear a single violin play a delicate note in a busy train station. And at first, if the hall were silent, you could hear the pure tone, and even the soft shiver that makes it musical. But the moment the crowd arrives, the footsteps, the whispers, the rolling suitcases, the fine shiver is swallowed by the noise, and all that remains to your ears is a plain, steady sound. This is the feeling of quantum decoherence told gently. because at the tiniest scales a thing can hold a both at once, shimmer called superposition, like a coin that is still spinning, and is heads and tails in the same breath. Yet the everyday world you live in looks ordinary and settled, because the environment is a crowd that rushes in and quietly steals the shimmer before you can notice it. Here is the simple picture you can carry like a bedtime sketch. A small system, say a grain of dust, an atom, or a little electric circuit touches its surroundings all the time, bumping into air molecules, soaking up warmth from nearby objects, scattering light from the room. And each tiny touch is a handshake that says, "I was here." And once the surroundings collect enough of these little "I was here" notes, the system's many gentle possibilities stop adding up like a neat chorus and start behaving like ordinary either or choices, not because the magic was fake, but because the delicate phases that let possibilities blend have leaked into all those handshakes with the world. If that feels abstract, think of colored soap bubbles floating side by side. When no breeze stirs them, their skins reflect light in patterns that can overlap and make shimmering rainbows. But when the air swirls and fingers poke and dust lands, the rainbow information is carried away in the tiniest smudges until the bubbles simply look dull. And in quantum language, the rainbow is coherence, the shared rhythm that lets alternatives interfere. And decoherence is the loss of that shared rhythm when the system becomes entangled with everything around it. Entanglement here is not a scary word. It just means the system and the environment keep a joint diary, a matching record like two friends who agree on what happened. So that if the system was in a blend of here and there, the environment now holds matching notes. I felt it here, and I felt it there. And because those two environmental notes point in different directions, their influence cancels the interference you would otherwise see if you looked only at the system. Importantly, nothing explodes or breaks when decoherence happens, and nothing chooses a single outcome by force. The world simply shifts from a superposition you could have noticed to a mixture that looks classical, because you never read the giant diary the environment wrote. And in practice, since that diary is spread into countless air molecules, photons, vibrations, and tiny jostles that remember the encounter. This is why big objects behave so well. A dust grain in sunlight scatters a storm of photons every instant. Each scattering is like the environment taking a snapshot of the grain's position. And after just a blink of time, far less than a blink, really the snapshots pile up so quickly that any both here and there shimmer has been recorded in so many places that local interference is effectively gone. And what remains to you is a grain with a definite place. Even the shapes of the classical world have a story here. Some special sets of states are hardest for the environment to mess up. They are called pointer states because the environment keeps measuring them over and over the way a clock hand keeps pointing. And these stable states tend to be positions or well-defined patterns that survive the crowd's attention. So this is why you see objects sitting somewhere. Instead of seeing strange smeared combinations, the environment is a constant, gentle observer that favors certain clear stories. Now you might ask whether decoherence is the same as a measurement, and the kind answer is that measurement is just decoherence with a purpose. A big prepared environment, a detector, a camera, a screen that grabs the diary in a strong readable way and stores it in a stable record. While ordinary decoherence is the everyday version, where the diary is written into the room itself with no one reading it, page by page. This difference matters because it explains something subtle. Decoherence does not choose which outcome happens. It makes the interference between alternatives unseeable in practice. By spreading the phase information so thin that recovering it would mean reversing every microscopic splash your system made in the world. And that reversal is like unbreaking a million eggs at once. This is why quantum computers are kept cold and quiet inside shiny boxes. Their job is to keep that violin's delicate note alive long enough to play a piece, shielding the qubits from the crowd, correcting little stumbles as they go. Because the everyday world keeps trying to turn the living harmony into plain noise. It also explains why you cannot use quantum weirdness to send secret messages faster than light or rewrite yesterday. The environment does not help you cheat. It simply decides whether the stage allows a wave pattern to be heard or forces a clean footprint to be left. And once the diary is spread, the shimmer is gone for you, even though, in principle, the full universe's joint diary still contains it. If you want a child's handle to hold all this, try this line. Coherence is like two soft ripples that can meet and make neat rings. Decoherence is the wind that wrinkles the pond so the rings cannot appear. And classical behavior is just the way ripples look when the wind never stops. From this, a gentle life lesson grows without pushing that claw. In your day often depends on the context you keep. A quiet room lets you hear fine details and hold more possibilities before you decide. A noisy room makes you commit to simple choices quickly, and the universe works the same way at the smallest scale. It holds many maybes. When isolated and settles into neat either fails. When it talks to everything else, so when you breathe out now and picture your room, the lamp glow, the air, the hum of the street. Imagine all those tiny interactions as the friendly crowd that keeps your world steady, turning quantum music into the classical song you can walk to. And remember that beneath the calm surface, the notes are still capable of harmony when we learn to listen carefully, build quiet stages, and ask the world the kind of questions that let the shimmer be heard before the station fills with sound again. Virtual particles. Reality from nothing. Close your eyes and picture the quietest room you can imagine. The kind with soft walls and the lights turned low. And now imagine that even here, where you expect perfect stillness, the air itself has a tiny restless tremble, like a barely audible hum that never stops. That gentle hum is the doorway to virtual particles, a friendly but often misunderstood idea that says, empty space in quantum physics is not a hard perfect zero, but more like a calm ocean, whose surface still makes tiny ripples you can only notice with careful tools. And the first lesson for a child and a grown-up alike is this. When scientists say nothing, they usually mean a special something, the vacuum state of a field, which is the lowest energy, most relaxed arrangement, allowed by the rules, not a literal absence of existence. So if we speak softly, we can tell the right story without magic. The story that reality's quietest level still carries the possibility of momentary, rule-following flickers that help shape what we measure. Now take a slow step into that story by replacing the old picture of solid particles with a kinder picture of fields that fill all of space, one field for light, others for electrons and quarks. And in this picture, a particle is a splash or a packet of a field, like a note played on an instrument, while the vacuum is what you have when every instrument is tuned and silent, but still able to vibrate if touched. And virtual particles are not extra crumbs sprinkled into the room. They are the bookkeeping marks we use when calculating how fields nudge one another. The internal steps in a recipe that never appear on the plate, but still matter for the flavor. This is why physicists draw little diagrams with lines that go in, lines that come out, and faint lines in the middle, that begin and end those faint internal lines are called virtual, and they stand for tiny disturbances that are allowed by the math as part of the interaction. Short-lived hints that never travel to a detector on their own, and cannot be bottled, weighed, or photographed, yet leave a fingerprint on the final answer. If you have heard that all particles borrow energy from the universe and pay it back quickly, hold that claim with a very light grip, because the safer way to say it to a child is that quantum events have a natural blur in when and how we can describe them. And our calculations keep track of that blur with numbers that act like momentary detours, but the deep rules still protect the big laws. Energy, momentum, and charge remain conserved in every complete story. So there is no cosmic bank account flipping negative and positive to cheat the books. There is only a careful accounting that includes those hidden steps. Even though virtual particles themselves are not directly seen, their footprints show up in gentle, testable ways. They slightly shift the energy levels of atoms, changing the color of light they absorb by a tiny amount called the Lamb shift. They tweak the magnetic personality of the electron and the muon by a hair's width that we can measure with extraordinary precision, and they help explain why two mirrors placed very close together feel a faint push, as if the vacuum between them were sans. Queased effects that do not mean particles pop like rabbits from hats, but that the fields are alive enough to respond, and our formulas, with their virtual messengers in the middle, correctly capture that response. Here, it helps to learn a good habit of mind. Never confuse the map for the land. Virtual particles live on the map, our perturbation series, our diagrams, our integrals. And the land is the field itself, which remains the real actor. So when a teacher says a force comes from exchanging a virtual particle, the friendly translation is that the fields around two objects talk to each other. In a way our math can track, as if a messenger ran between them. A story that gives the right numbers, even though no tiny courier ever arrives at a camera. This careful attitude also protects you from common fairy dust in popular stories. Like the idea that black holes evaporate because one virtual particle falls in and the other escapes. A picture that can be a useful cartoon for a first taste, but is not the whole meal, since the precise explanation is about quantum fields living in curved space-time, and how their definition of which vibrations count as particles changes near a horizon, producing real radiation that can be calculated without pointing to a single virtual pair. At the same time, it would be unkind to swing to the other extreme and call virtual particles fake. Because when you run the numbers that include these internal steps, you match experiments again and again with breathtaking accuracy. So the right bedtime wisdom is that virtual particles are like scaffolding around a building, never part of the house you move into. But without them, the structure could not have been assembled with such clean lines. Perhaps the most important gift you can carry from this room is a better sense of nothing. The vacuum is the calmest possible state of every field together, a state that still allows tiny fluctuations the way a sleeping cat still breathes. And when something disturbs that calm and electric charge, a magnet, a boundary like a metal plate, the pattern of allowable trembles shifts, and the results we can measure reflect that shift, which is why the seeming emptiness of space quietly shapes the behavior of atoms, light, and matter at every moment. If you are a child listening for a single sentence to hold on to, try this. Virtual particles are the polite whispers in the math that help two things talk, not little marbles that pop out of nothing and run around on their own. And the whispers matter, because they change what we hear in ways we can test, and there is a tender life lesson in that too. Because much of what guides your day is invisible in the same way habits, expectations, the rules you and your family agree on, they are not objects you can drop on the floor, but they shape what truly happens, and learning to respect those quiet influences makes you wiser. So as you breathe out and we close the door on this room, remember that reality from nothing is really reality from the rules. A calm vacuum filled with fields ready to answer, and our virtual guests are the penciled notes between the lines that let the final song come out exactly right. Not magic tricks sneaking around the laws, but careful harmonies that keep the laws true while letting the world be subtle. And that is a wonderfully steady thought to carry into sleep. The Casimir effect, empty space, creates force. Imagine laying two perfectly smooth metal plates, so close together that a grain of dust would be too fat to slip between them. A silent alley only a few dozen billionths of a meter wide. And then discovering a tiny gentle push that tries to slide the plates toward each other. Even though there is no motor, no spring, no glue, just empty space. This is the Casimir effect. A soft surprise that teaches you that emptiness in physics is not a hard zero, but a quiet room full of possibilities. And the plates act like librarians who suddenly change which whispers are allowed to echo between the shelves. So the hush inside the gap is different from the hush outside, and that difference adds up to a real force. Here is the friendliest way to see it, without heavy math. Light is not only the bright stuff from lamps and stars, it is also a sea of tiny jittery field ripples that can, in principle, wiggle at many sizes and rhythms. And when you place two conducting plates face to face, you tell those ripples, only the wave patterns that fit perfectly between us may live here, like guitar strings that only sing certain notes when you press them at the ends. Outside the plates, the ripples can take almost any size, big and small notes mixed together, but inside the narrow gap only a subset can stand. And because fewer notes are allowed inside than outside, the outside pushes a little harder than the inside, the same way air pressure is higher outside a vacuum flask than inside. And that gentle imbalance nudges the plates inward. If this feels too airy, picture a child's harp that you slide into a smaller and smaller box. Each time the walls come closer, fewer strings can vibrate freely, and the music inside gets simpler and quieter, while the music outside the box stays full and loud, and the loudness difference is like a pressure that leans on the walls. The Casimir push is most noticeable when the gap is tiny shrink. The distance by half, and the force grows a lot. Shrink it again, and it grows dramatically. So in real laboratories, people use careful setups with gold-coated plates, torsion balances, and ultra-clean rooms, and they watch for the faint twist of a lever or the subtle drift of a microscale spring to catch the effect. A force smaller than the weight of a dust mite, but steady and predictable enough to measure. To keep the story honest and simple, you don't need to imagine particles popping in and out like rabbits. You can stick with the standing wave picture. The world's electromagnetic field is everywhere. Boundaries pick which wiggles can exist where, and counting the allowed wiggles inside and outside tells you which way the net pressure leans toward attraction for two simple flat, conducting plates in a vacuum. Now, because nature loves details, the sign and size of the Casimir effect can change with materials, shapes, and even the stuff in the gap, with special coatings, with a fluid between surfaces, or with quirky geometries, like spheres near plates. The force can weaken, shift, or in rare engineered cases, even become repulsive. And at warmer temperatures, slow, long wavelength wiggles add their own small contribution, so the effect sub-Li depends on heat as well. None of this breaks conservation of energy, or creates power from nothing. The plates and the field together form a system, and as the plates move, the allowed spectrum of wiggles changes, trading energy with mechanical motion in a way the equations carefully keep balanced, like a seesaw that always accounts for where the weights sit. For tiny machines called MEMS, which live at the scale where nanometers matter, the Casimir force is both a friend and a nuisance. It can cause stiction, where little parts stick together when they shouldn't. But clever engineers can also harness or dodge it by choosing shapes and coatings that tame the invisible push, turning a mysterious quantum whisper into a practical design factor. If you want a bedtime picture that you can hold in your hands, think of two combs faced toward each other, with a thin sheet of silk between them. If the silk were a sea of possible ripples, then bringing the combs closer blocks more and more ripples from forming in the silk between. And the outside silk, still full of ripples, presses the combs together. Scientists test this story by changing the gap, polishing the plates, cooling the room, swapping materials, and comparing the measured push to the predicted one. And again, the numbers agree within tiny margins, strengthening the simple lesson that boundaries shape the quiet of space, and the quiet pushes back. This effect also connects gently to other corners of physics without repeating old tales. The same count the allowed modes logic helps explain why hot objects glow the way they do, why cavities make lasers behave, and why the color of light in a tiny box is not the same as in open-air boundaries curate, which notes the electromagnetic field may sing. If you're wondering whether this means we can build a free energy machine by just letting plates clasp together forever, the kind answer is no. You must do work to pull them apart again, against the same force. And after one full in-fay-out cycle, you are back where you started, like winding and unwinding a spring, with no extra gift hidden in the loop. The child-sized moral of the Casimir effect is beautifully modest. Emptiness is textured when you give it edges, and the act of drawing a boundary invites the fields of nature to rearrange their invisible rhythms, leaving tiny, measurable fingerprints on the things you can touch. And there's a life lesson folded inside that is not about physics at all. Sometimes the quiet between people, the spaces you keep, and the limits you set shape what can happen just as powerfully as any loud action. And paying attention to those soft boundaries can bring calm order where random noise would have been. So when you drift to sleep, you can imagine the two silent plates, the narrow alley of nothing between them, and the gentle, persistent nudge, born from letting only certain notes live there. And you can smile at how the universe turns even stillness into a story that moves things ever so slightly toward each other. Hawking radiation, black holes evaporating through quantum tricks. Imagine the darkest thing you can picture so dark that even light, the fastest messenger you know, cannot run away once it crosses a certain invisible edge. And then let yourself be surprised by the gentlest twist. That very darkness can glow. This is the quiet wonder of Hawking radiation, a story where black holes, those one-way gates of gravity, slowly leak warmth into the universe. Not by magic or cheating, but because the rules of the tiny and the rules of curved space meet at the horizon and make a soft fire where you thought there could be none. And we will keep it as simple as a bedtime whisper, while still teaching you something new to hold. Start by imagining the event horizon as a shoreline. You cannot step back across, a place where time and space are tilted so strongly that all paths point inward. And now remember that what we call empty space is not a hard zero but a calm sea of fields that can be stirred into little ripples when pushed. And near a horizon the pushing is extreme. Clocks far away and clocks skimming the edge do not tick together. Light stretching out there looks different from light measure did here. So even if nothing dramatic happens at the horizon for a brave swimmer falling in, the faraway watcher reads the situation with a different ruler and hears a faint hiss of heat leaking outward. The easy cartoon you may have heard says pairs of particles pop from nothing. One falls in, the other escapes, and becomes the glow. But a kinder, truer picture for a child is this. The field around the hole has many ways to wiggle, and gravity at the horizon mixes the wiggles we call positive with the wiggles we call negative. So that what looks like a calm chord to someone falling can sound like a warm note to someone far away. And that warm note carries energy. No law is broken energy. Conservation stays tidy, because the energy that climbs out is paid for by the hole's mass, making the hole ever so slightly lighter. And that slow loss is what we poetically call evaporation. There is even a simple rule of thumb that you can keep without numbers. Small black holes glow more, big black holes glow less, because the temperature of the glow is inverse to size, like a drum that gets a higher pitch the smaller you tighten it. So a tiny black hole would be hot and bright, while a huge one, like the ones at galaxy centers, would be colder than the glow of the universe itself, and would swallow more background light than it gives off. This is why no astronomer sees giant black holes steaming like kettles. Space around them is still warmer than their own Hawking warmth. Yet the principle remains solid, tested not by catching the whisper from a cosmic giant, but by checking many connected ideas in labs and theory, like how particles behave for observers who accelerate, how horizons of different kinds change what counts as a particle, and how the mathematics that predicts black holes should glow also explains why ordinary hot objects radiate with a spectrum whose shape we know, if you could shrink a black hole enough, keeping it perfectly alone and quiet. The story would speed up. Each little bit of mass lost makes the hole hotter, which makes it lose mass faster. A slow, then suddenly quick ending, like a candle that smolders most of the night and flares at the last second. But for anything formed by the collapse of a star, the times are so long, they make ages seem like minutes, so no one will watch one vanish over breakfast. The beauty of Hawking's insight is that it blends two languages without forcing them to marry completely quantum fields for the small curved space-time, for the heavy, and even with that modest truce. It gives a clean, testable prediction, an exact temperature, a gentle glow, and a steady leak of energy outward, as if gravity itself were charging a tiny fee for holding a horizon. The story does not need you to believe in little marbles jumping out of nothing, or in stealing from the bank of energy. It only asks you to accept that what counts as a particle depends on how you watch, and a horizon forces different watchers to disagree in a lawful way that leaves a real trace: light. Now there is a riddle tucked inside the glow that keeps grown scientists awake at night, and should make you curious rather than afraid. If the radiation looks random and warm, like steam from a teapot, where does the detailed information about what fell into the black hole go? Does the universe misplace it, or is it woven into tiny correlation in the light that are hard to see, or is the surface of the hole more like a memory, keeping screen that slowly drips the story back out? Or must a deeper theory of space and time teach us new rules for how information hides? You do not need to choose tonight, because this puzzle lives at the frontier and many roads holographic ideas, quantum error, correcting pictures of geometry, clever thought experiments with entanglement are being walked with care. But the original warmth Hawking found remains the campfire at the center, the thing any true path must keep. So what should you carry with you as you breathe slower? First, that a black hole is not simply a mouth that eats and stays silent forever. It is also a very patient whisperer, letting energy go in a way we can describe without myth. Second, that small can be hot and big can be cold for reasons gravity makes precise, and that your everyday sense of empty fails near horizons, because empty depends on how you measure. Third, that the universe is kinder than it seems, offering clues at the edges of its scariest places. So a perfect darkness becomes a teacher of light. When you close your eyes, picture the horizon as a quiet shoreline again, the sea stretching inward endlessly, the sky above full of stars, and feel how the faintest glow rises not from breaking the rules, but from the rules embracing each other at the boundary, and let that be a gentle thought to fall asleep with. That even the heaviest secrets brighten the world when you learn how to listen. Quantum cosmology. Did the universe tunnel into existence? Picture a universe that begins not with a bang you could have heard, but with a hush that rolls open, like morning fog lifting from a field, and imagine that before there were stars, or clocks, or even space to point at, there was only a rulebook waiting, quiet and complete. The way the instructions for a game exist even when the board is still in the box. Quantum cosmology asks a tender question inside that hush. Could our whole cosmos have appeared the way small things sometimes do in the quantum world, by slipping through a wall that ordinary logic says is too high to climb? Not by breaking a rule, but by following a deeper one called tunneling, where possibility sneaks past impossibility like a shy fish gliding through reeds. To feel this without heavy words, remember a marble at the bottom of a bowl, safe in its little valley and a short hill between it and the open tabletop. Classically, the marble needs a push to get over the ridge. But in quantum land, a very small marble can show up on the other side. Now and then, because the rules allow a gentle smear of maybes that sometimes carry it through. And when physicists wonder about the universe itself, they imagine a similar story told with different pieces. Instead of a marble, there is a single number that measures how big space is. Call it the scale of the universe. And instead of a wooden hill, there is an energy shape made from gravity and the contents of space, a shape that makes very small universes stuck and larger universes free. And the question is whether the whole thing could have tunneled from the stuck side to the free side, landing in an expanding phase that grows into everything we see. Two friendly pictures carry this idea. Both careful, both simple enough for bedtime. One is the tunneling proposal, which says the probability flows outward into growing universes the way ripples move away from a splash, as if the cosmos popped out of the rulebook into a state where space is already on its way. The other is the no boundary picture, which says the universe did not start at a sharp edge at all. It is more like the roundness of the Earth at the North Pole, where asking what is north of the North Pole is the wrong kind of question, because north ends there, and in this picture, the earliest slice of reality is a smooth cap that has no before, with time unfolding only after the cap rounds into the familiar kind of space we move through. Neither picture uses magic dust. Both use the same gentle trick that works in ordinary quantum life. You calculate the weight of different possibilities by summing over paths, and sometimes the best path is not the one that follows the usual clock, but one that bends the clock sideways for a moment, like drawing a shortcut on tracing paper before laying the paper back on the map. And the result is a tiny seed of a universe that can inflate stretching space smooth and wide in a blink so that galaxies have room to grow and the sky looks almost the same in every direction. A child might ask what "from nothing" really means here, and the kind answer is that it does not mean from empty hands. It means from a state with no classical space and no ticking time, but still with the rules of quantum gravity in place. A stage with no scenery yet, but a script that can be read. And there is even a soft way to see how energy is not being stolen. In general relativity, the energy stored in gravity itself can be counted as negative while matter and light are positive, and in very rough terms the two can balance, so that the total is close to zero, like a perfect loan that cancels debt with savings, leaving you free to start a project without breaking the bank. Why should anyone believe a bedtime story about the biggest thing there is? Because parts of it echo in the patterns we measure. A tunneled or no boundary seed that inflates tends to produce a universe that is nearly flat, with tiny, almost scale-free ripples that later become galaxies. And those predictions fit the faint mottling in the cosmic microwave background that satellites have mapped, a quiet checkerboard of small ups and downs that tells us about the first whispers in the cosmic air. Yet we must be honest and gentle with limits. Many different beginnings can lead to similar ripples after a long expansion, so the data is suggestive rather than final, and the deepest equations here, which blend quantum rules with curved space, are still being learned like a difficult lullaby, whose last notes we cannot yet sing without wobbling. You might also worry about time itself, because if the earliest stage is timeless, how did ticking begin? The friendliest answer is that time can be relational, born when one part of the universe plays clock for the rest, and once the seed becomes large enough that many things can point to change light, temperature, density, then before and after blossom naturally, like the way a melody appears when you hear enough notes in order. You might also ask whether tunneling a whole universe is just a metaphor stretched too far from small experiments. And the right response is that it is a cautious extension, made in a trimmed-down model, where only a few degrees of freedom are kept, like a toy train that helps you understand tracks, without building an entire railroad. And physicists are careful to check whether the toy's lessons survive when you add detail. One real comfort in these ideas is that they are consistent with the rule that nothing travels faster than light to tell the seed what to do. The smoothness after inflation does not require distant regions to talk in a forbidden way, because the stretching connects them from an earlier, smaller stage when they were neighbors. And there is a second comfort hidden in the word tunnel. It does not mean the universe slips through a solid wall like a ghost. It means that the probability of finding yourself on the other side is not exactly zero when the rules allow a path that was classically banned. And even if that probability is tiny, all it takes is one successful nudge, when there is no clock to count the tries. Because how long did it wait is not a sensible question before time is born. To hold all this gently, you can keep 3 simple sentences. The rulebook may have allowed a seed universe to appear by a lawful quantum step. The seed was set up so that rapid stretching smoothed it and filled it with structure. And the glow we see today in the sky keeps only faint memories of that step. Just enough to suggest, but not enough to prove. The grown up work ahead is to connect this lullaby to a full theory of quantum gravity. One that can tell us exactly which seeds are allowed and why. And to look for tiny signatures in the sky that would favor one beginning over another, like a hidden watermark in ancient paper. Until then, you can fall asleep with a steady thought that is both humble and exciting. Perhaps reality did not need a giant shove to begin, only permission written into its own laws. And from that permission, a seed that tunneled into openness could inflate into the grand room you live in now, with stars scattered like lanterns. And you here to wonder how the first light ever learned to glow. And if that is true, then the most astonishing thing about the universe is not that it started loud, but that it started lawful. A quiet yes at the edge of nothing that grew into everything you can name. The holographic principle. Reality as quantum information on a surface. What if the inside story of the world could be written on its skin, like a very neat label, that somehow contains everything about what's inside the jar, where every swirl of the liquid, every tiny seed, Every scent is recoverable from the writing on the glass. That gentle question is the doorway to the holographic principle. A careful idea that says in some deep sense the information needed to describe a region of space might live on the boundary that surrounds it. And you can hold this without getting lost if you picture a planetarium dome that shows a whole sky on its curved surface, while you sit underneath and feel as if you're inside a vast night. The points on the dome are not pretending to be stars. They are a different way to present the same scene, and just like that, physics whispers that the world might allow two faithful descriptions. One in the bulk, the three-dimensional interior we move through, and one on a surrounding surfaces, made of tiny information pixels that together can capture the interior's story. The clue that pushed scientists toward this bold thought came from black holes, which behave like perfect safes for information and have an odd rule for how much can fit inside, because their maximum information grows with the area of the horizon, not the volume inside, which is as strange as a library whose book capacity depends on the size of its walls rather than the floors of its rooms. So if a black hole's information scales with surface area, maybe nature as a whole organizes information in a similar boundary first way to make this friendly for a child. Imagine covering a spherical balloon with very tiny squares, so tiny you can barely see them, each square able to hold a single yes/no bit, and the rule says the number of squares on the skin. How many of these bits you can fit sets the ultimate limit on the detailed story you can tell about what's inside. Not because the inside is fake, but because the skin is enough when used with the right code, in special, curved like a bowl universes, that physicists can study with clean math. This wild idea becomes precise. Everything happening inside with gravity can be perfectly translated into a gravity-free quantum system, living on the edge, and everything on the edge can be translated back into the inside. Like two languages that say the same poem without losing a rhyme, so a star's collapse, a beam of light, even a tiny ripple in space-time, all have matching sentences in the boundaries language. The glue that makes this work is quantum entanglement, the same kind of deep linking that lets two particles share a relationship no matter how far apart they drift. And here you can think of space itself as being stitched by patterns of these links, so that when you slice the interior into two parts, the amount of linking between the parts, the how many threads cross the cut, is reflected by how much boundary length or area you must cross on the surface. A quiet rule that says the area of a certain minimal loop on the bound measures how entangled the interior pieces are, which is a little like saying the number of friendships between two neighborhoods is written into the shape of the fence that divides them. This shed light on another old worry about black holes. If a hole evaporates by giving off warm light, where does the detailed information about what fell in go? Because it seemed to vanish forever, and that troubled people who love tidy bookkeeping. Yet the boundary picture suggests the information never truly disappears. It is scrambled in a very careful way across those surface bits, more like a secret woven into a large quilt than ink spilled into a drain. And because the boundary description is a special kind of error-correcting code, you can even lose some of the bound patches and still recover what happened inside, which is a reassuring hint that the universe keeps faith with its stories, even near its strangest edges. None of this says we are living in a fake video game, and it is important to keep that straight for young ears. A hologram sticker doesn't lie about the image it shows. It is using a different method to encode the picture, and the holographic principle is like that. A statement about dual descriptions that carry identical physics. Not an invitation to roll your eyes at reality. So when people say, we live on a surface, the kind reply is, we might be able to describe our world from a surface, which is a beautiful but different claim. What makes this more than poetry is that the boundary theory where gravity disappears, and only quantum fields and their entanglement remain, lets us calculate things that would be hard inside, like how strongly a very hot fluid pushes back when stirred, or how fast it relaxes when perturbed. And then we compare those answers to behavior we observe in heavy ion collisions or exotic materials. and the numbers line up closely enough to keep us curious. At a deeper level, the principle nudges you to see geometry itself as a kind of ledger of relationships. Distances and curves in the interior can be reconstructed from the pattern of quantum links on the boundary. So space becomes less of a stage built first, and more of a tapestry woven from information. And if you adjust the linking pattern, you adjust the interior shape. The way rearranging the knots in a net changes the size of the holes to keep things calm. Remember that we do not yet have a full holographic map for our entire real universe, which is not shaped like the neat bowl, where the math is cleanest, but the lessons travel. Surface area counts information more naturally than volume in gravitational settings. Entanglement knits space, and the right code on a boundary can protect and recover the interior's content, all of which gives scientists clues for building a theory where quantum rules and gravity are not rivals, but partners speaking the same tongue. A child can carry 3 simple images without strain. First, a balloon whose skin holds tiny pixels that together are enough to describe the air inside. Second, a fence whose shortest path tells you how many friendships cross between 2 yards. Third, a quilt that hide a long story in a scrambled pattern that can be fully read if you know how to piece the squares. And none of these images require you to believe in tricks, only in careful bookkeeping. From here, a soft life lesson unfolds that suits bedtime and waking. The edges of things matter more than you think, the boundaries you draw in science. In art, in your day, shape what can be known and how safely it can be kept. And often the summary written on the outside, if crafted well, is enough to rebuild the living heart within. So as you breathe out, imagine a starry vault overhead, and the feeling of being held under it, not fooled, but embraced by a different way of telling the same sky, and let the quiet idea settle that perhaps reality's richness can be carried on a skin of information without losing its depth, and that learning to read that skin is part of growing wise in a universe that is generous enough to offer more than one faithful way to know it. Quantum consciousness hypotheses. Is mind a quantum effect? Imagine holding a snow globe of your own mind and wondering whether the sparkle inside is ordinary glitter swirling in warm water, or something stranger, a shimmer that needs the rules of the very small to make sense. And as you tilt the globe gently, you ask a brave question a child might also ask: is consciousness a quantum effect? Does the feeling of you depend on the same delicate physics that lets tiny things act like waves and choose among possibilities in ways big things never do? To explore this without getting lost, keep 3 soft lanterns in your hand. What would count as quantum in a brain? What would make that quantum activity matter for inner experience? And what kinds of signs have scientists actually found? And then walk forward step by step. First, what does quantum really mean here? Not just that atoms are quantum, because everything is made from quantum parts, but that some brain process might use unusually delicate patterns like coherence and entanglement, where many possibilities are kept in step, as if they were singing the same note, long enough to change how information is handled. In ordinary life, those fragile patterns fade fast in warm, busy places. And a brain is warm and busy on purpose, full of salty water, bumping molecules, and electrical chatter. So if a quantum mind exists, it must either find sheltered pockets where the dance can survive, or use the Bach soul itself in a clever way. People have offered several kinds of ideas. Some say consciousness itself is tied to a special kind of quantum event, as if awareness lights up when a wave of possibilities settles in a very particular way. Others say the brain performs tiny quantum computations that enhance what neurons can do, turning parts of the cell into microscopic logic devices. And others still suggest quantum randomness slips into decision-making and gives choices a spark that pure clockwork could never offer. Let's make those simple and kind. The first family says mind is not just what the brain does. Mind is what happens when certain quantum events become facts. Almost like the world blinking from maybe to yes, and your awareness riding that blink. The second family says the brain might host small protected circuits, perhaps inside the cell's scaffolding called microtubules, where quantum patterns can live long enough to be useful, helping the brain spot shortcuts or store rich associations more efficiently than a classic on-Fay-off network. The third family says, even if you can't keep DELIC 8 patterns alive, the tiny random kicks allowed by quantum rules might wiggle neural thresholds and keep the brain from becoming a dull machine, building a style of freedom out of a sea of microscopic surprises. Each family has reasons to hope and reasons to doubt, and you can learn from both without getting tired. Start with the microtubule idea. Neurons hold long, hollow tubes made from repeating proteins, and some propose that the electrons inside these structures can share vibrations like a well-tuned choir, supporting quantum patterns that spread along the tube, with the bold claim that when these patterns self-stabilize or end, they line up with moments of experience, like tiny lanterns switching on and off in a cathedral. What pushes back is the environment, because even a whisper of heat and bumping molecules tends to scramble delicate patterns faster than a neuron can use them, on timescales far shorter than the thousandth of a second rhythms seen in brain activity. So if the tubes are to help, they must be unusually well shielded or arranged in clever repeating ways that protect the pattern, the way weaving protects a thread. Experiments have looked for signs of long-lived coherence in brain, like conditions, and the story is still cautious. We have proof in nature that quantum patterns can survive briefly in warm, messy settings. Light harvesting molecules in plants show wave-like energy sharing for tiny slices of time, and certain birds sense Earth's magnetic field by pairs of molecules whose spins dance in step. But those successes are tuned for their special tasks, and do not by themselves make a mind. So the burden is to show similar, sustained behavior linked to neural function. What about the idea that a special kind of quantum event is needed for awareness, with your now tied to wave settling in a way no machine could simulate? It is an intriguing doorway, but it trades one mystery for another, because you still have to explain why that event feels like seeing red or remembering your name. And you must check that the proposed special event fits with well-tested rules in labs, where calculations using ordinary quantum theory already work astonishingly well without needing a new kind of collapse at brain scales. And what about quantum randomness as your spark of freedom? It certainly prevents your brain from being perfectly predictable, but unpredictability alone is not the same as agency, the feeling that you chose for a reason, and many thinkers suggest that the useful kind of freedom is not raw coin, flip noise, but the way a huge, richly connected network, your brain, can balance stability with flexibility, settling on decisions through dynamics that are sensitive to tiny differences, yet shaped by memory and goals. So quantum noise might season the stew without being the chef. None of this leaves you empty-handed, because along the way you learn what a brain must do. It must integrate information across regions. It must keep signals reliable over long distances and times compared to the scale of molecules. And it must remain robust to bumps, while still being reconfigurable at will. And classical mechanisms already accomplish a lot of that. Synchronized rhythms, long axons, feedback loops, and chemical messengers form an orchestra that plays beautifully without requiring hidden quantum instruments. Yet the door is not shut, because quantum biology keeps surprising us with pockets where nature does use the small world rules to squeeze extra performance from light, from magnetism, from enzymes. And it is reasonable to ask whether evolution might also use such pockets in neurons for speed or sensitivity, even if those pockets do not carry the full weight of consciousness. The clean path forward is to ask for fingerprints. And fingerprints can be simple. Can we design tests that look for non-classical correlations in neuronal signals that cannot be faked by classical noise? Can we perturb suspected structures in a way that would kill coherence if it exists while leaving ordinary function intact? Can we build artificial circuits in the lab that swap a classical component for a truly quantum one, and see a clear, reliable boost in tasks that resemble perception or working memory? Just as important is honest accounting with timescales. Mind-level events live in milliseconds, while quantum events flicker in femtoseconds and picoseconds. So any useful quantum contribution must be coarse, grained into slow, stable variables that neurons can use. And that requires a clear mechanism for storing and reading the delicate patterns without crushing them. A tall order, but not a logical impossibility. For now, the safest bedtime sentence is this: your brain certainly runs on quantum matter, yet current evidence suggests you do not need long-lived quantum computers in your head to think, feel, and choose. Although nature could be borrowing small quantum tricks here and there to make certain steps a bit more efficient. If someday the fingerprints arrive, signatures of entanglement in living neural tissue, repeatable links between controlled quantum states, and changes in perception, devices that mimic those states and win at mind-like tasks, then the snow globe will look different and we will rewrite the textbooks with joy. Until then, it is wise and exciting to hold two ideas at once, without letting them fight. The classical story of neurons and networks is already powerful, and keeps making accurate predictions about attention, memory, and action. And the quantum story is a set of open hypotheses that must earn their place with crisp tests, not just with pretty metaphors. And here is a gentle life lesson, hidden in the science. You do not lose wonder by demanding evidence. You honor it, because the mind you want to understand is the same mind that learned to be careful with its own wishes. And that care has given us lasers, MRI scanners, and the ability to read the light of the first stars. So as you breathe out and rest the snow globe on the shelf, you can enjoy the sparkle without forcing it to be fairy dust, knowing that whatever the final answer is, quantum spice in a classical stew, small hidden engines in microtubules, a brand new rule we have not written down yet, it will still be your mind discovering it, and that may be the most magical part of all. The quantum Zeno effect, watching freezes motion. Have you ever tried to watch a soap bubble so intensely that you almost will it to stop shrinking, as if your careful gaze could hold it in place for one more breath? The quantum Zeno effect is the quiet version of that wish come true, not by magic, but by the way tiny things respond when we keep asking the same yes or no question too quickly to let them change. And the heart of it is simple enough for a child, a system that would normally move from this to that, like an excited atom that would usually relax and give off a little flash, can be pinned near this if we check again so fast that the beginnings of the move are constantly interrupted and reset, like trying to learn to ride a bike while someone taps your shoulder every single second and asks, "Are you still sitting?" forcing you to put your feet back on the ground before the first wobble becomes a glide. The name comes from an old puzzle about an arrow that never seems to travel if you only look at frozen snapshots. But here, the freeze is not a word trick. It is a real physical effect in the very first instance of change. Quantum rules make the chance of leaving the starting state grow only very gently, slower than your everyday expectation. And if your measurements arrive inside that tender window, each one acts like a tiny reset to start. So a long string of resets can hold the system close to home for far longer than it would have lingered on its own. To keep it clear, watching in this story never means a human stare. It means a probe that touches the system just enough to find out, are you still the same? Because in the small world, asking is a kind of touching, and touching, even gently, ties the system to the probe and leaves a mark that prevents the delicate first steps of motion from building up into a real change. As if you kept opening the oven to peek and the cake never got a steady stretch of warm minutes to rise. Real experiments make this picture concrete. Students trap a single ion in a quiet chamber, nudge it toward a transition that would normally happen, and then pepper it with rapid queries that shine a tiny pulse and read still excited. The more often the query, the more stubbornly the ion refuses to budge. People do similar things with cold atoms caressed by laser light, with superconducting circuits that behave like artificial atoms, even with molecules headed toward chemical rearrangements. And the same rule of thumb holds if the question is strong enough to count as a measurement and comes faster than the system's natural rhythm of change. The change slows or stalls. This is not a loophole in the laws or a way to cancel time. It is a lesson about beginnings. Because quantum change does not leap instantly, it grows from a tiny seed, and a measurement plucks out that seed before it sprouts. There is a friendly cousin to this effect that teaches the opposite lesson too. If you nudge and check at an intermediate pace, not so fast that you always reset, not so slow that you ignore the system, your pokes can actually help the change along. An anti-Zeno effect where your attention becomes a rhythm that encourages the move, like clapping in time to help a friend keep walking. So the moral is that observation is not a neutral spectator in the small world. It is a participant whose timing shapes the dance. For technology, this matters in two opposite ways that both help us think clearly. On one hand, if you want to protect a fragile quantum memory from wandering away, you can engineer gentle, frequent checks that keep it aligned. Sometimes by coupling it to a monitor that constantly asks a harmless question, and the watchfulness becomes a shield. On the other hand, if you need a system to move along a chosen path without getting stuck in wrong steps, you can design a pattern of soft measurements that discourages the bad moves and allows the good ones, like painting subtle, do not enter signs along the wrong corridors of a maze, steering without pushing. The careful part is remembering that a measurement always involves a touch, and touches take time and can add noise. So in practice, there is a sweet spot. Too slow, and the system ignores you. Too fast, and you smother it with overhead. Just right, and you shape its fate. If you want to understand the math without carrying symbols to bed, keep one clean sentence. In the very short run, the chance a system has left its starting state grows like a tiny curve, not like a straight line. And if you measure before that curve has time to bend upward, you flatten it again. So many quick flats add up to nearly no progress. This is why a continuous, gentle monitoring, almost like resting a hand lightly on a spinning coin, can act like friction that keeps the coin from tipping into a new face. And it is also why decoherence from a noisy environment sometimes looks like the world measuring too often, washing away delicate evolution into plain behavior. A child may worry that this means we can freeze anything by simply paying attention. But the kind truth is that your eyes alone do nothing special. You need an interaction that leaves a trail in the world, a photon reflected from an atom, an electrical signal in a circuit, a mark in a detector, and you need to repeat it faster than the system's own heartbeat. Otherwise it will change between your checks, and you will only learn that you were too late. There is a soft philosophical echo here worth holding lightly. Sometimes in life, hovering prevents growth, and stepping back allows motion, but the physics lesson is sharper. Change is not continuous in the way your gut expects at the smallest scales. It begins with a fragile start that can be reset. And that makes asking a tool, not just a way of knowing. With that clarity, you can appreciate the surprise without getting spooked. The quantum Zeno effect does not contradict cause and effect. It refines it, telling you that causes delivered as constant interrogation can suppress their own outcomes, and that the timing of your questions is as real a knob as the strength of your pushes. And when you are ready to sleep, let the image be simple and calm. A metronome about to swing, a gentle finger tapping the arm at just the right moments, so the swing never gathers, the room quiet, the device patient, and you understanding at last that in the small world, watching is a way of touching, and touching in the right rhythm can hold a moment still long enough for you to see how beginnings actually begin. The measurement problem. When does reality happen? If you tap a camera's shutter in a dim room and the picture jumps from a soft smear to a crisp scene, you can point to a click and say now. But in the quantum world, the question, when does the crispness happen, refuses to sit still. And that unease is the measurement problem. A tiny thing evolves gently, as if many possibilities are alive together. Then a single outcome appears on a detector. So at what moment And by what rule does maybe become is? To keep this friendly, imagine a toy that acts like a miniature compass flying into a magnet. The theory says its wave can split into two quiet streams. One up, one down. Like two soft lanes of fog. And a screen with tiny counters waits to register a dot. Yet the equations that carry the fog forward do not contain a command that says, pick one lane. They simply keep both lanes in step until the counters are included. And when you include the counters, and the wires, and the computer that stores the dot, the very same equations say the world becomes a larger entangled state where lane up is tied to counter up and lane down is tied to counter down. A careful super story with two incompatible records that never talk. You and I never see such a double record. We see a single dot, a single report. So we draw an imaginary line, the cut between system, an apparatus, and add a rule before the cut. Smooth evolution at the cut. A jump to one outcome. And while this recipe predicts the right statistics, it hides the part we are asking about, because the cut can be slid around without changing numbers, which feels like explaining a magic trick by saying, somewhere off stage it happened. You might hope the busy surroundings settle it. And there is truth there. The moment the counter's atoms talk to air, light, and heat, the delicate phases that let the two fog lanes overlap are dispersed into a billion degrees of freedom. So interference between the two big stories becomes unseeable. This is decoherence, a natural sorting that makes one counter-image not mingle with the other. But notice what it does and does not do. It tells you why the mixed stories stop interfering. It does not tell you which story becomes your lived experience. It is like a teacher wiping the board so that only one line of the homework can be read at a time without smearing, while never telling you who chose that line. Different answers step forward here, each simple enough to sketch before sleep, and different enough that you learn something new from each. One answer says nothing ever jumps. The universal state continues its smooth duet, and what you call outcomes are branches that no longer exchange notes once decoherence spreads. In this many-world style picture, there is no single when. There is a local, very fast branching whenever small differences get amplified. Your brain, the air around them all become correlated with either up or down, and your experience is of one branch because you too have been copied into those non-communicating stories. Probability then is not magic dust, but a rule about how often branches with certain weights appear for observers who count a subtle point grown. Up still debate, but the child-sized idea is calm. The movie never cuts, it just splits into screenings that never share a theater again. A second answer says nature really does snap, gently but physically, adding a small extra ingredient to the equations that makes large, spread out possibilities unstable, so that one crystallizes at random with precise odds. In these objective collapse ideas, a detector or any sufficiently heavy extended thing triggers a genuine jump. So, when is once amplification crosses a threshold. And this is testable if we build interferometers for bigger and bigger objects, giant molecules, tiny crystals held in light. They should, at some size, stop showing delicate patterns earlier than mere environmental jostling would predict. Experiments keep pushing that size upward, tightening the net around how strong such spontaneous snaps could be. And that is how a bedtime story earns the right to stay on the shelf, by sticking its neck out to be measured. A third answer walks a quieter road by giving particles definite positions all along, while letting a guiding wave choreograph their paths, like small boats moved by an unseen current. In this pilot wave view, there is never a question of when for the particle. It is always somewhere, and measurement is simply the moment your apparatus magnifies where it was into a visible record, while the wave in a larger, sometimes non-local sea steers the outcome frequencies to match the familiar quantum odds. You learn here that what is real can mean both the boat and the water are real, and the mystery shifts to how widely the water's influence reaches, which is strange, but not self-contradictory. A fourth answer says the very idea of one global moment for reality is a trap. A quantum state is a user's manual for an agent, a careful book of expectations about experiences, and measurement is the update of that book when an experience lands. In this agent, centered or relational view, when does reality happen becomes, when do I, the agent, register an outcome, and there is no requirement that two agents who have not compared notes must share a single story yet. This does not deny the world. It relocates certainty to the places where records are actually read, has the virtue of matching how laboratories function, and it prunes paradoxes born from mixing declarations made from different vantage points, as if they were one. What all four teach without repeating old metaphors is that the word when hides other words you must choose first. When relative to whom? When according to which rule? When at what scale of amplification? And when after which interactions have made alternatives unable to interfere, the rest follows. You also learn that properties in the small world are often questions made precise, rather than stickers, things where in advance. A point called contextuality, proven in games where any attempt to assign answers to all possible questions at once leads to contradictions. So the world gently insists that outcomes belong to the act of asking with a specific tool, not to an object in isolation. That is not wordplay. It is a map for building experiments without confusion. If you want a concrete sense of scale, the time from first contact to effectively classical record can be astonishingly short. Atoms in a solid need only trillions of a second to imprint a passing electron's choice into many neighbors. So for everyday apparatus, the happening outruns any human interval, which is why our world feels crisp, yet the knife edge between still reversible and for all practical purposes decided can be widened or narrowed by temperature isolation and design, giving engineers room to build both whisper, sensitive quantum devices and loud, dependable detectors. The soft closing thought is this: the measurement problem is not a monster hiding in physics. It is a mirror teaching you to speak carefully about facts, perspective, and scales. It reminds you that reality does not owe you one universal timestamp for every event, and that what you call now it happened is either a branching you joined, a physical snap you can in principle test, a magnified position revealed, or a moment of experience you record. For honest ways to hold the same world steady in your hands. And as you let your breathing slow, you can trade anxiety for curiosity, feeling how kind it is that a single click on a screen can open such different, consistent stories, and that you are free to use anyone as long as you promise to be faithful to the questions you asked and the records you kept, because in that promise lies the simple piece of science. The universe does not stutter, it answers. And our task is to learn how to hear the answer we truly ask for. The quantum brain puzzle. Can neurons exploit superposition? Imagine trying to balance two piano keys pressed at once so the sound is both notes together, while a whole orchestra plays around you, and every vibration wants to jostle your fingers. That picture is close to the quantum brain puzzle you're holding now. Could a neuron keep a tiny both at once state called superposition long enough to matter? Or does the warm, busy concert of the brain immediately nudge it into a single ordinary note, fire or don't fire, to walk in softly? Remember what a neuron actually does. It listens to thousands of whispering inputs along its dendrites, each whisper a small flow of ions that nudges the cell's voltage a little up or a little down. And at one special neck of the cell, the axon hillock, the neuron decides whether to launch a traveling electrical pulse, the action potential, a fast all, nothing spike, that runs along the axon to its partners. Under a classroom microscope, this looks classical. Charges move, voltages change, thresholds are met. Messages go, yet down near the molecular floor, the parts of that machine are quantum objects. Ions filtered through narrow channels only atoms wide, electrons shifting between energy levels, protons hopping within hydrogen bonds. And that invites the daring question, could any of those tiny quantum-flavored steps place the whole neuron into a superposition of about to spike and about to stay quiet? And could that superposition be kept alive long enough, then amplified, so your thought truly uses it? The first gentle obstacle is timing. Superpositions keep their special phase only if nothing leaks information about which alternative is which. But inside your head, water molecules bump everything. Proteins flex, ions collide, and thermal motion at body temperature makes the world an excellent gossip. Any hint of which way tends to spread quickly. Meanwhile, the neuron's decision window is slow by quantum standards, and the elementary quantum jitters in channels and receptors live on timescales millions to billions of times shorter. So to help the neuron, they must either repeat in a disciplined pattern or be collected and stored without losing their phase. A tall order in salty, moving fluid. The second obstacle is size. A superposition that matters has to involve enough of the membrane potential that it can tip the threshold, which means coordinating many charged particles. Not just one, and every extra participant is another handle for the environment to grab and dephase. So the default expectation is conservative. Neurons behave like robust, noisy analog, digital devices whose small parts are quantum, but whose overall computations can be modeled well by classical equations with little random jitter added. Yet default is not proof. And there are niches where quantum effects could still sneak in and matter without turning the brain into a delicate qubit farm. For example, in ion channels, the selectivity filter is so narrow that ions sometimes move in single file, and their passage is helped or hindered by tiny energy differences that quantum mechanics controls. In enzymes that shape neural chemistry, short-range tunneling of protons or electrons can speed reactions in ways that classical pictures underestimate. At synapses, the decision to release a vesicle of neurotransmitter depends sensitively on a handful of calcium ions. Tip the count by very little, and a vesicle may or may not fuse. So molecular scale events can get amplified into a send or don't send at the next cell. The key is not whether such steps are quantum in origin, but whether they preserve superposition in a way the neuron can use. And that means two tasks. Keep coherence long enough to influence a threshold, and funnel that influence into a macroscopic difference reproducibly. Most likely, the brain uses the first part, but rarely achieves the second, because the very coupling that lets small events drive big outcomes, strong electrical interaction with the membrane, heavy ionic currents, rapid diffusion, is the same coupling that lets the environment read out. Which alternative too soon? Still, you can ask for fingerprints instead of opinions. And they can be simple and kind. One test looks for non-classical temporal correlations in a single neuron, the kind that violate certain inequalities if a state truly explores incompatible alternatives before a readout. Another test uses isotope substitution in carefully chosen molecular steps, and watches whether spiking statistics shift by amounts that outpace what ordinary chemistry predicts. A third line builds artificial neurons, where a genuine quantum element, say, a superconducting qubit, or a solid state defect with controllable coherence, feeds a threshold circuit, and asks whether tasks involving ambiguous, rapidly changing stimuli get a measurable boost that cannot be mimicked by classical noise with the same statistics. And there are softer no tests too. Cool tissue a little, quiet some. Noise sources, stabilize temperature gradients. If coherence were hiding, these changes should help it last longer and show up as altered timing or reliability. But if nothing systematic appears that weighs the scales toward classical explanations, don't worry that any of this would yank freedom or magic away from your choices. Brains already achieve rich, flexible behavior by balancing stability and sensitivity in giant networks, where small differences, regardless of origin, can be amplified when and where the system is poised near a decision boundary. Quantum randomness, if it enters, is just one source of those tiny nudges among many. And the music of agency is written by how the network uses memory, goals, and feedback to turn nudges into reasons. There is also a practical moral to carry into tomorrow's labs. Even if neurons do not store superpositions, engineering measurement, aware protocols around them can help. Arranging stimulation and recording so that you don't constantly unintentionally measure away subtle intermediate states can reveal dynamics normal methods blur. And designing molecular probes that minimally disturb ion channels lets you separate true kinetics from the footprint of your own tools. A lesson borrowed from careful quantum experiments, but useful everywhere. Step back now and breathe. The quantum brain puzzle does not demand that your thoughts ride on fragile waves the way a qubit does. It invites you to see where the small world rules do and do not survive inside warm tissue. And it rewards you with clearer questions either way. If coherence can be tracked and harnessed, we learn new biology and build new kinds of sensors. If it cannot, we still learn exactly why the brain chose the materials and rhythms it did, preferring reliability and recoverable randomness over brittle elegance. And the soft closing thought is this: you do not need to drain the wonder from your mind to be rigorous about it. You can let the orchestra keep playing while you notice that half-pressed keys blur in a crow. That single plucks can still shape the whole melody, and that the marvel of a neuron is not whether it is secretly a quantum computer, but how it turns countless uncertain pushes, molecular, electrical, and social, into the steady, meaningful patterns that let you listen, doubt kindly, and choose. Free will versus quantum randomness. Are choices truly ours? Imagine your mind as a small bakery after hours. The mixers are quiet, the dough rests under clean cloths, and you, the baker, stand between two recipes you know by heart. One for cinnamon rolls and one for soft pretzels. And the question you ask is not which pan jumps off the shelf by itself, but who chooses what goes in the oven, which is a child's way of asking the grown-up puzzle. Are your choices truly yours? Or are they just sprinkles of quantum randomness landing on a batter that would otherwise bake itself without you? Begin gently by separating two ideas that often get tangled: randomness and freedom. Because quantum physics really does contain true randomness, the kind that not even the smartest calculator can predict in advance, as when a single atom decides when to emit a tiny flash, or a radioactive grain sets off a detector with a click you cannot foresee. And this unpredictability is real and important for science, but if you poured it straight into the bakery, it would not bake, meaning it would scatter flour on the floor. Choosing is different from chancing. When you pick cinnamon rolls because your friend loves them and you want to see her smile tomorrow, there is a reason shaped by memory and care. And if a hidden device under the counter randomly turned the dial to pretzels, that surprise would not feel like your decision. It would feel like a prank. So the first lesson is simple and strong enough for a child. Noise is not will. Still, the story does not end there. Because your brain is not a stiff machine. It weighs tastes, imagines smells, remembers last time's mess, checks the clock, hears the rain outside and thinks warm, and in that busy weighing there is both structure and sensitivity. A kind of graceful balance where small nudges can matter at the edge of a decision. Here, quantum randomness can enter as a whisper, not as a boss. Tiny fluctuations can tip a neuron here or there. Break a tie when two options are almost equal. Help you explore instead of getting stuck. And yet the important point remains that you are the one who set the table, where such whispers matter, because you built values and habits and plans that define what counts as a good outcome, much as a baker decides that soft and fresh are goals before any coin is flipped. Some people worry that if the universe had a perfect clockwork beneath everything, freedom would be an illusion. But think of control instead of fate. When a bicycle follows your hands and leans with your body, its motion obeys physics all the way down. Yet it is still true that you steered, because you means the whole organized system, the nervous system, the muscles, the training that turns reasons into action, whether the micro details carry a dash of randomness or line up like gears. The level at which you live your life is the level that asks, compares, vetoes, and commits. And that level is not erased by what happens in the basement. Laboratories have tried to peek at this basement to kitchen handoff in quick artificial tasks. Signals in the brain can ramp up before you report feeling a decision, which sounds like the brain decided before you did, but notice how these tasks work. They are about pressing a button, whenever, with no stakes, no recipes, no reasons, while the choices you care about unfold over seconds, minutes, days, with back and forth checking, imagining outcomes, waiting for more information. And there you often change your mind, delay, or cancel, which is itself a kind of decision. This is not a trick to rescue pride. It is a reminder that while "ooh" are not a beep heard at the end, you are the whole process that sets goals, gathers evidence, and can say no at the last instant, a capacity scientists call control, and you can feel its reality when you decide to put the knife down and breathe before speaking. Even though the first push of anger had already started, to keep it practical and kind picture. 3 roles at once. The world offers constraints. Your body and brain provide capabilities. And within those limits, you exercise agency, which is the power to respond to reasons, not to conjure outcomes from empty air. Now fit quantum randomness back into this picture, in a way a child can hold. Sometimes you let a die choose who gets the last cookie, when fairness matters more than preference. Sometimes you shuffle songs, because surprise is the point. And in those moments, randomness is a tool you use, like a wooden spoon, not a ghost that uses you. The deeper you look, the more you see that meaningful freedom depends less on whether the universe flips coins, and more on whether you can act from a stable story about yourself. Values you endorse, commitments you remember, consequences you accept. And that story lives at a scale above atoms, the same way a melody lives above individual air molecules. Even though it rides on their motion, if everything were pure randomness, life would feel like being pushed around by gusts you never asked for. And, if everything were rigid like ice, you could not adapt. But in between there is a sweet spot. Call it responsiveness, where reliable structures make your plans possible and gentle unpredictability keeps you flexible. Science even builds machines on this principle. When exploring a maze, adding a tiny sprinkle of randomness helps the robot avoid dead ends. Yet the map, the goal, and the backtracking logic still belong to the robot's design. You work the same way, except your map includes kindness, memory, and taste. There is one more worry to soothe before sleep. That if choices are caused, they are not free yet. Caused by what I believe and want after thinking is exactly the kind of cause you hope for, because the opposite is either chaos or compulsion. Free will in this calm view is not the power to float above physics. It is the everyday power to make your actions answer to reasons that feel like yours and survive scrutiny tomorrow, and it can be stronger or weaker, depending on attention, knowledge, and the health of the systems that support you. That means freedom grows with practice and can be protected by design, sleep, habit, and honest feedback. Make better bakers and better choosers, while stress, fatigue, and noise make anyone more random in the bad sense. Carry, then, 2 simple sentences that do not fight. Quantum randomness is real, but randomness alone does not make choices. Your agency is real, because you are a layered, learning creature who can shape which signals matter and why. And let the closing image be quiet. The kitchen lights dim, 2 trays ready, your hand steady on the oven door, the rain tapping the window, and you, after weighing what you know and who you are cooking for, deciding to bake cinnamon rolls and setting a timer, not because a coin whispered, not because the world was forced, but because you became the reason this sweet smell will exist in the morning. The no cloning theorem. Why quantum states can't be copied. Imagine walking into a quiet workshop at night and finding a strange photocopier on the table that claims it can duplicate anything perfectly, from a paper crane to a soap bubble, and you lean close and whisper, "Could you copy a single quantum state for me? This tiny qubit that's like a coin still spinning." The gentle answer, which is both surprising and important enough to build a whole field on, is no. In the quantum world, there is no universal way to make a perfect copy of an unknown state, and this is called the no cloning theorem. a rule that sounds strict but turns out to protect communication, keep eavesdroppers honest, and shape how we design quantum machines. Begin with what copy means in a child-friendly way, with ordinary information, a picture on paper, a file on a computer. You can make duplicates because the thing you're copying can be read without changing it, like photographing a mountain that doesn't notice the camera. A quantum state is different because it stores not just a this or that, but a delicate recipe of possibilities and phases, the quiet timing that lets waves add or cancel. And when you try to read that full recipe, you inevitably touch it in a way that changes the dish. So any plan to say, whatever arrives, I'll make two of it runs into trouble the moment you ask for details. There is a clean, almost storybook reason why physical laws in quantum mechanics preserve angles between states, meaning if two states are somewhat alike, neither the same nor completely opposite, that how alike number stays the same after any allowed evolution, but a copier that takes 1 becomes 2 would accidentally square that likeness, turning pretty similar into even more similar, which would rewrite the rules of geometry the theory insists on. The only times that squaring doesn't break things are when the two states were either identical or perfectly different to start with. Which is why you can build devices that clone a small known set of alternatives. But you cannot build a single machine that, without knowing the recipe, duplicates every possible state. A softer way to feel the same point is to picture trying to copy a scent that you aren't allowed to sniff. You can't draw the exact bouquet into another room without first taking a sample, and sampling is enough to disturb the perfume you were trying to preserve. This is not a scolding from nature, it is a protection. If perfect quantum photocopiers existed, a sneaky listener could steal secret keys in quantum cryptography by cloning every flying qubit and measuring the spare at leisure, and two far apart friends holding entangled particles could amplify a faint choice into a loud message faster than light by cloning over and over, which the universe forbids to keep cause and effect steady. The theorem clarifies one more easy to misunderstand point. It doesn't stop you from recreating a state you already know. If you have the recipe, you can bake as many cookies as you like by preparing fresh systems the same way. But it blocks you from taking a single, unknown cookie and stamping out identical twins without first learning its inner pattern. You might ask whether careful measurement could sneak around the rule by peeking a little. But partial peeks only give partial information and leave you with an approximate clone, never a perfect one. People have built such approximate cloners in the lab, and they work exactly as the math predicts. Their copies are good but not flawless, and the best possible accuracy is capped by the same geometry that forbids perfection. The no-cloning theorem also explains why quantum error correction looks different from ordinary backup plans. Instead of making many exact duplicates of a qubit, we hide its delicate recipe across several physical systems by WEPs, Wigner entanglement, so no single piece knows the whole story. But the pieces together can recover it if a few are disturbed. Like spreading a sentence across several envelopes, so that losing one doesn't lose the meaning. Related wisdom shows up with no broadcasting, which says you cannot even distribute all the information from a fuzzy, mixed quantum state into many places at once. Again, because trying to do so would let you distinguish states too well and break the geometry. There is a bright positive flip side. When you need to move a quantum state from here to there, you don't clone it and pass the copy, you teleport it, which is a polite protocol where the original is purposefully destroyed while its full recipe reappears elsewhere, using entanglement and a couple of ordinary bits so that no two perfect versions ever coexist. The difference between cloning and teleporting is the difference between multiplying a secret and relocating it, and only the second is allowed by the rules. If all of this still feels abstract, imagine a librarian who handles a single fragile manuscript that smears when touched. The library can make high-quality summaries by reading, but the act of reading changes the ink a little. To preserve the exact text, the librarian stores the information across several transparent sleeves, in such a way that damage to one sleeve can be fixed by consulting the others. And if the book must travel, the librarian disassembles the sleeves and reassembles them in a new location using a coded courier. Never two perfect books at once. The deeper you look, the more you see how much this one theorem quietly organizes the world we are building. It guarantees the security of quantum key distribution, because an eavesdropper cannot duplicate signals undetected. It sets the boundary between classical repeaters, which amplify signals by copying, and quantum repeaters, which must use entanglement, swapping, and purification to extend reach without ever making clones. It guides how we design measurements, reminding us that if we want to preserve a state for further use, we must measure gently and only along compatible questions. Otherwise, we collapse the very structure we hope to copy. And it teaches a gentle life lesson too, because the most precious things about you, your exact state of mind in this instant, the particular way your memories and feelings are braided, cannot be duplicated without changing you. Not because of mysticism, but because information with phase and context is not a stamp but a living arrangement. As you let this settle, notice the calm pattern behind the headline. The no-cloning theorem is less a wall than a map telling you which roads are safe, prepare known states, share entanglement, encode across parts, teleport instead of copy, and which temptations lead to contradictions. And the soft closing thought is this: there is kindness in the fact that uniqueness is protected at the smallest scales, that the universe keeps certain recipes from being multiplied without understanding, and that building with those limits in mind doesn't shrink our power, it focuses it, letting us craft messages no thief can duplicate and computers that compute without leaking their secrets. Quiet, precise work in a workshop where the magical photocopier is replaced by something even better. Tools that respect the delicate things they handle. The quantum information paradox. What happens inside black holes? Imagine tossing a handwritten diary into the darkest vault in the cosmos and hearing, to your shock, a slow whisper of heat leaking back out, as if the vault were also a low, patient furnace. And the real question that grabs your sleeve is not does the diary burn, but does its story survive? Because in quantum physics, the deepest rule is that processes are, in principle, reversible. The world's tiniest equations don't like perfect erasers. That is why the quantum information paradox feels like a knot tied in the middle of your thinking. A black hole forms. You feed it matter with a detailed history, letters, patterns, quantum states, and decades or eons later, it glows and shrinks by emitting what looks like random thermal light. And if that glow is truly featureless, then the diary's information would be gone for good, which would break the rule of reversibility. But if the information is not lost, where can it be? Tucked behind a horizon no one outside can read, or braiding itself into the outgoing glow in a code so subtle you wouldn't notice until you knew exactly how to listen. Start gently. Information here is not gossip. It is the precise recipe that would let a perfect physicist rewind a process and get back the starting state the way a careful cook could reconstruct a soup from a flaw. Less record of every swirl and spice, Hawking's original calculation, done with quantum fields near a curved horizon, said the glow depends only on the hole's mass, spin and charge, a plain-looking spectrum like heat from a stove. And if you count the uncertainty of that radiation, the curve only climbs. The more the hole evaporates, the more random the outside looks, until the hole is gone. A final shrug that seems to say, the story is ash. Yet quantum theory demands a different shape called the page curve. Entropy should rise at first, but then reach a crest and fall back to zero by the end, like a secret that seems scrambled at first, and then, with enough pieces, begins to make sense. How could that happen? Here, a kinder picture appears. Black holes are not silent trash compactors. They are extreme mixers, fast scramblers, that blend new pages with old ones, in astonishingly few steps, once a black hole has passed its halfway point in evaporation. The page time, fresh information you to SS in can, in principle, start leaking back out quickly in the radiation that follows. Not legible line by line, but hidden in correlations across many distant photons. A trick explored in thought experiments by imagining you already hold the early glow in a hard drive, and then watching how little extra you need to decode the new addition. But there is a fierce catch called monogamy of entanglement. The late photon streaming away from the whole seems, in one story, to be paired with a partner just behind the horizon, while in the information comes out story the same late photon must be paired with many earlier photons far away. A single quantum cannot be perfectly paired with two different partners at once. So which pairing is real? One blunt answer says, the horizon must not be gentle. There is a firewall. A violent curtain ending the smooth fall, yet that tramples the calm prediction of general relativity that big horizons feel ordinary to the infaller. A subtler answer, called black hole complementarity, says no single observer can check both pairings. So there is no operational contradiction. The infaller experiences the smooth inside pair, the distant decoder experiences the far-away pair, and nature never lets one person gather both proofs at once. More recently, careful calculations using simple quantum gravity models draw an even clearer map, with lands when you compute how much randomness is in the radiation. The region you must count as belonging to the radiation can unexpectedly include a slice of the black hole interior, an island, so the partner of a late photon is effectively part of the outside's accounting. The math of these islands produces exactly the right page curve, up crest, down again, rescuing reversibility without burning the infaller. What then happens inside? The soft but radical answer is that inside may be an emergent way of organizing information, rather than a separate stash of atoms. The interior's smoothness for a falling observer is woven from entanglement among many degrees of freedom. And as evaporation proceeds, that entanglement gradually migrates into the radiation, far from meaning the inside doesn't exist. It means the inside is encoded, like a play that lives in the shared memory of its audience as well as on the stage, so that with enough of the outside light and the right decoding, parts of the interior can be reconstructed from afar. This is not empty poetry. The same mathematics that lets a boundary theory faithfully describe a bulk region also shows up here in a quantum error, correcting way where the information about the center is redundantly and safely spread over many edge pieces, protecting it from loss, and eventually letting it be recovered when you gather enough pieces. Other gentle ideas decorate the picture. Subtle, soft charges on the horizon that record angles and phases of what fell in, or the suggestion that entanglement can be pictured as a thin bridge linking systems that share a secret. But the test every story must pass is the same. Do you get the page curve? Do you keep the infaller comfortable? And do you prevent anyone from sending messages faster than light or copying unknown quantum states? So far, islands and their kin are winning that quiet contest of consistency. And where does that leave you? The person who wanted to know about the diary with a reassuring lesson. The universe seems to hate true shredders. It prefers secret keepers. So black holes are less like bonfires and more like obsessive archivists that encrypt everything. They swallow, mixing it so thoroughly that only by collecting an enormous fraction of the outgoing glow and using the right keys could anyone recover a page. We have not yet built the device that would do such decoding, and no telescope will watch a big black hole complete its long final whisper. But the maps we draw agree across many routes, and they teach you to be precise about words. Lost can mean hidden beyond practical reach, which is not the same as destroyed. And that difference keeps quantum theory whole. As you let this settle, feel how the paradox, instead of being a wall, became a lantern. It forced us to ask what inside and outside really mean, how space might be stitched from correlations, and why the darkest places may, in their own spare way, be the most faithful librarians the universe has. Returning not ash but code, slowly, steadily, and only to those patient enough to gather the light and learn the language. Quantum entanglement, instant links across the universe. Pretend you tie a ribbon around two spinning tops, and then carry them to opposite ends of a quiet playground. And when you pull the ribbon away, the tops keep their own lives. Yet somehow a hidden rhythm remains, so that whenever you cup your hands over each top and ask the same gentle question, "Are you pointing this way or that?" your answers match more closely than any secret plan could guarantee. That soft picture is how to hold quantum entanglement in your mind without getting tangled. It isn't a whisper line for messages, and it isn't magic mind reading, it's a rule about togetherness, a pattern so tight that the results of separate measurements fit like two pieces of one puzzle, even when the pieces are far apart. And to see why this matters, you start at the simplest place, with a pair made together. A burst of light in a crystal that produces two tiny photons, or two electrons that dance for a moment and fly off, so that the combined state is prepared as one whole, and then you let them drift. If you look at just one partner alone, its outcomes are as random as coin tosses, and you cannot predict any single click. But when both partners are measured, and the notes are later compared, the randomness shrinks into a sharp pattern that depends on how the questions were asked. A pattern so strong that no stack of pre-written, "If asked this, answer that" instruction cards can reproduce it consistently, no matter how cleverly you shuffle them or how well you hide them. Experiments have pushed the labs far apart, switched the questions at the last instant, and still the correlations hold, which tells you that the connection is not a late signal sprinting between stations, but an earlier, deeper knitting in the way the pair was made. To keep this gentle for a child's ear, think of the tops as two spinners with colored wedges, and your question is a line you lay across each spinner at any angle you like. Then you ask, "Psi me side of the line or opposite?" and you mark yes or no. If the spinners had only agreed on a limited set of answers in advance, there would be angles where their agreement could not beat a certain safe limit. Yet real entangled pairs surpass that limit in just the way the quantum rules predict. And they do it without letting anyone cheat the speed of light, because each side by itself still looks like noise until the notebooks meet. This difference, shared pattern without shared message, is the heart you must protect from confusion. Entanglement gives you correlations stronger than any local pre-planned story, but it cannot be used to send news or win lotteries. And that is why you can have instant links without paradoxes, like two books printed from the same masterplate, that reveal a hidden acrostic only when you lay pages side by side under the hood. The mathematics tells you that the pair is described not by separate recipes for each partner, but by one joint recipe in which certain combinations are definite, while the parts alone are not. And that is why trying to assign each partner a neat list of answers for all future questions leads to contradictions. The practical lesson is friendly. Entanglement is a resource. Like a special thread, you can weave into tasks so that separate devices behave as if they share a clock, a ruler, or a sense of direction better than ordinary setups allow. And people use it to sharpen measurements of time, to link distant sensors so their noise cancels, and to build the bones of future networks where delicate quantum states can be moved, checked, and protected. If that sounds abstract, keep one workable image. You and a friend each hold a deck of transparent cards, printed with faint patterns. And when you overlay a card from your deck on a card from your friends at matching angles, a hidden picture pops out with extra clarity. No extra ink was sent across the room. The clarity was stored in the way the two decks were made, and only revealed by aligned choices. There is kindness in the rules here too, because entanglement cannot be copied at will, and it cannot be peeled apart into smaller secrets without losing power. So using it demands care. Align your questions thoughtfully. Protect the pairs from noisy bumps that would let the environment read them first. And remember that if you try to squeeze out too much detail from one partner alone, you will spoil the shared recipe you wanted to use. You may wonder whether this hidden ribbon means everything is secretly arranged long before we ask anything. But the experiments that flip settings quickly and separate stations widely tell us that no ordinary hidden plan living at each site can explain the results. And that makes entanglement not a conspiracy, but a clue that the world's bookkeeping is done in joint ledgers, rather than individual diaries when systems are born together. Used well, this clue becomes a tool. You can distribute pairs between far labs and verify that no eavesdropper has touched them. Because any meddling weakens the very pattern you depend on, and you can swap entanglement so that two partners who never met become linked through careful middle steps. A bit like two musicians who never rehearsed together, falling into harmony, because each had rehearsed with the same conductor earlier. What you should carry out of this, especially if you are small and curious, is not the idea that thoughts jump across space, but that questions asked in the same way at both ends of a shared story produce answers that fit together more snugly than any two separated stories could. And this snugness is testable, countable, and useful. It also nudges a soft philosophical thought that won't keep you up at night. Perhaps separateness is sometimes a choice of description rather than an absolute fact. And when things have grown from one seed, a part of their identity lives in the relation itself. Still, you do not need poetry to be amazed. The data itself is wonder enough. Clicks on distant counters that, when plotted together, draw curves no classical dice can mimic, and the closing comfort is simple and warm, like a nightlight. Entanglement is not there to spook you. It is there to teach you that togetherness has rules deeper than distance, that nature keeps perfect score when systems are made as one, and that by asking clear, matching questions you can reveal a harmony that was present all along. A quiet ribbon that ties outcomes into patterns. You can trust even when the tops spin far apart under different skies. Quantum tunneling, particles crossing impossible barriers. Stand before a garden wall you built from blocks of damp sand, solid to your hands, and sure enough to stop any marble you roll. And now imagine a thin, silver fog drifting toward that wall, and, to your surprise, finding itself on the other side without cracking a single grain. This is the mood of quantum tunneling, where a particle that seems too small and too tired to climb a barrier can still be found beyond it. Not by cheating or smashing, but because in the tiny world a particle is also a spread. Outwave and waves can leak through slivers of space, in a way your everyday ballast and bricks never do. To carry this gently, say to yourself, a barrier is just a region where the particle is energy would make classical motion impossible, like a hill that's taller than your run up. Yet the quantum rulebook never sets the wave to exactly zero inside that hill. It only lets the wave fade exponentially. So if the hill is thin enough, a faint echo of the wave still survives on the far side, and wherever wave exists, there is a chance, however small, to find the traveler. Nothing illegal happens. Energy is not borrowed and returned like a secret loan from the universe, because the particle's energy remains the same on both sides of a still barrier. And what changed was your willingness to accept that being somewhere comes from a wave that can seep into places where motion would not roll. This softness has hard consequences you can touch. Deep inside some heavy atoms, a little cluster of 2 protons and 2 neutrons wants to leave. Yet the nuclear forces pen it in with a steep energy wall, and still, after a certain waiting time, that cluster is suddenly gone and later seen outside as an alpha particle. The chance of slipping out depends exquisitely on the thickness and height of the wall. Double the thickness, and the chance shrinks not by half but by huge factors. Which is why a small tweak in the nucleus can stretch a half-life from minutes to ages, and why geologists can read time from rocks by counting these rare, rule-following escapes. The same quiet trick keeps stars alive. The Sunday is not hot enough for 2 positively charged protons to bulldoze through their electric repulsion by sheer speed. Yet fusion happens because tunneling lets them overlap and bind now and then, turning a too-cold furnace into a patient one, where many tiny improbabilities add up over vast numbers to make light. And in your own hands, if you've seen pictures of atoms that look like ball bearings on a table, those come from a device that listens to tunneling, a needle brought absurdly close to a surface, closer than a virus is wide, feels an electron current that jumps across the empty gap, not by flying like a pellet, but by tunneling like our fog through sand. And because that current depends exponentially on the distance, a change smaller than a single atom's size makes a big change in current, letting the instrument draw the surface atom by atom. Engineers use the same idea to store and erase data in flash memory by letting electrons tunnel through a very thin glassy layer into a tiny trap, and in superconducting circ, Wootters pairs of electrons tunnel across a thin insulator in step, Josephson tunneling, making devices so sensitive that they can measure magnetic fields from your heartbeat, and also serve as the atoms of quantum computers. None of these rely on lucky magic, they rely on the strict math that says a wave that faces a barrier will partly reflect and partly transmit, with the transmission probability falling off like a steep cliff as the barrier grows wider or higher, and peaking again if a cavity is carved between two barriers at just the right size. So the wave resonates like a flute resonant tunneling, suddenly letting many travelers through at one energy while keeping others out. A trick used to sculpt current in special diodes. If you wonder how long the slip-through takes, the answer is truthful and kind. It depends on what you mean by takes, because timing a process that has no well-defined path is slippery. Experiments with ultrafast clocks suggest that for electrons, it can be as brief as a handful of attoseconds, and different definitions of when emphasize different parts of the journey, but all agree that nothing outruns light and no message rides the tunnel to shout back in time. You can feel the physics without symbols by holding three small pictures at once. First, a violin string that is lightly pressed at the bridge still hums on the far side, faintly but not to zero, because vibrations spread. Second, a filter made of slats that muffles most wind, yet lets a soft draft through if the slats are in and the gaps aligned. Third, a keyhole that does not admit your hand, but lets the scent of cinnamon find you in the hall. In each, the impossible is only impossible for lumps, not for patterns. And in quantum mechanics, particles are both. This is why we do not use tunneling to walk through walls for a person. The barrier would be unimaginably wide, trillions upon trillions of atomic layers, and the wave's echo on the other side would be so tiny that you would wait far longer than the age of the universe to see it happen once. But for an electron facing a barrier just a few atoms thick, the echo is not tiny, it is workable, and that is the doorway by which modern sensors, memories, and qubits step. There is also a calm warning folded into the wonder. Because tunneling depends exponentially on thickness, devices that rely on it must be built and kept with care. One extra angstrom of oxide, one stray vibration, one smear of heat, and the current you expected can vanish into reflection or swell too large and damage the piece. So designers learn to treat thin as a living number, not a wish, if you like names. You can say that alpha decay was first explained by a scientist who treated the barrier like a fog bank and calculated a unnelling factor. That fusion rates in stars follow a similar steep dependence called a gamma factor, and that the currents in Josephson junctions march to an equation that turns a phase difference, the alignment of two superconducting waves, into a measurable flow. But you don't need the labels to hold the lesson. Barriers select. Thickness matters more than your classical gut expects, and the world's smallest travelers are unafraid of quiet, narrow darkness. All of this lands gently on a life thought that stays after the numbers fade. Sometimes the straight on push truly won't work, and the right move is to find the thin place, to let your effort become a patient wave that seeps rather than slams, keeping its rhythm through a narrow passage until the other side appears. And when you lie down tonight, if your mind starts building walls around hard questions, remember the silver fog and the sand, the star that burns because of improbable slips, the pictures of atoms traced by currents that leap across emptiness, and feel how the universe whispers that impossible often means unlikely unless you are small, steady, and the barrier is thin. A rule as useful for circuits and stars as it is for worries that yield not to force but to calm. Repeated touch. Bell's theorem. Local reality might not exist. Set two little weather huts on far hills under a quiet sky. Give each hut 3 windsocks, it can point in different directions, and let 2 friends inside. So far apart they cannot shout choose. At the last instant, which windsock to check. Then write down only one simple answer each time. The cloth flips this way, or the cloth flips that way. Now imagine you later put the notebooks together on your lap and discover that the matches between their answers are too strong to be explained by any ordinary plan made in advance. And that is your doorway to Bell's theorem. A calm but radical statement that if the world is both local, nothing you do here pushes there faster than light, and realistic, then those notebooks can never show the level of agreement you just saw. Yet real experiments do, again and again, which means at least one of those comforts must give. To feel why without heavy math, pretend the huts are allowed to agree on a private instruction list before being pulled apart. A stack of cards that tells each hut what to answer for each windsock direction it might later be asked about. And you, being clever, can show that any such card stack strategy obeys a hard ceiling on how often the answers can match across all the mixed choices. This ceiling is Bell's inequality, a simple bound laid across the sky, like a straightedge. Quantum mechanics, though, writes a different kind of instruction. Not a separate recipe for each hut, but a single joint recipe for the pair together. A recipe that does not fill in what each hut has for every possible question ahead of time, but still guarantees definite, crisp answers when a particular question is asked. And when you compare those answers, you find them correlated beyond the straightedge limit, just as the theory predicts. Perhaps you worry that the huts cheated by secretly signaling during each test, but the timing is arranged so that the choices of windsock are made so late and so far apart that no light-speed message could cross the gap in time. And modern setups push this even further by using fast random switches, long optical fibers or free space, and distant coin flips drawn from physical noise to pick the questions, closing door after door where a mundane influence could reap in. You might also think the trick lives in the sensitivity of the detectors, that maybe they only recorded a friendly subset of trials and skipped the rest. But teams have designed measurements that catch nearly every event, or they use different particles whose clicks are easy to count with high confidence. And the same strong pattern remains as you hold all this like a bedtime puzzle. Listen to the theorem's quiet voice. No story in which faraway objects carry pre-written answers to all possible future questions, and then reveal them locally without whispering across the gap, can fit the data, so you must loosen something. You can loosen locality and accept that influences stretch in ways that ordinary space-time does not show on its surface, though you must keep those influences from letting anyone send a controllable message faster than light. Or you can loosen realism and say that properties do not sit there finalized before you ask. The questions you choose help create which properties become facts, not by magic but by how the world's joints are cut. So there is no master ledger of what would have happened for every question you might have asked, but didn't. A third path relaxes the idea that your last instant choices were fully free of hidden nudges, suggesting that the randomizers and the particles share a subtle common past that prearranges the outcome statistics, but protecting this path from becoming an all-purpose conspiracy is hard work. And experiments have even used ancient starlight to steer settings, pushing any such prearrangement back across hundreds of years. So the coincidence would have needed to be written in the cosmos long before the devices were built. Through all these possibilities, one anchor remains. The theorem itself is not a guess. It is a proof about patterns any local, pre-written card story must obey. And nature simply steps beyond that pattern in ways our instruments can count. What then do you learn that is fresh and tender enough for a child to keep? First, that separateness is sometimes a choice of description, more than a fact of the world's bookkeeping, because when two things are prepared together as one pair, their later answers are parts of one joint sentence, not two independent diary entries. Second, that asking is not neutral. The kind of question you pose matters, and there is no hidden page in the back of the notebook that already contained the answers to the questions you didn't ask. Third, that even when togetherness runs deeper than distance, the universe remains kind about causality. The stronger than classical pattern cannot be turned into a faster than light telephone. It lights up only when the notebooks are finally compared, like a hidden image that appears only when two transparencies are laid together. From this you can step into real uses without losing the hush. People harness Bell's pattern to certify private keys with device. Independent security, where the very strength of the correlations is the proof that no eavesdropper could have copied the signals. And they build entanglement swapping relays that link distant stations into a quantum network, without ever letting a cheating, local realist script explain the data. You also gain a way to think in life that is both precise and gentle. Sometimes the world will not let you attach definite labels to everything at once. What it would have been if I'd asked differently. And wisdom means accepting that some truths come only in pairs, in relations revealed by how you look. None of this drains the wonder from the night. It just tunes it. Because when you close your eyes, you can picture the two weather huts again, their windsocks choosing angles with a playful chime, their pencils scratching left or right. And you can feel a small bright calm in the idea that reality is not a pile of separate stones, but a woven cloth whose pattern shows only when pieces are held together the right way. A cloth that refuses old strategies, yet never tears the rules of time. And that is why Bell's theorem is not a scarecrow but a lantern. It does not say chaos wins. It says our picture of local reality was too stiff, and that letting it relax reveals a world that is both stranger and more orderly than we guessed, where distance is not permission to forget that some stories begin as one. The EPR paradox. Einstein's spooky action at a distance. Picture a long, polished track in a quiet school gym. Two toy carts pressed nose to nose against a spring at the center, and imagine that when you release them they shoot apart like polite twins. One left, one right. Now suppose you're allowed to choose at the last second which tool to use on the cart near you. A ruler to read where it is, or a speed gun to read how fast it's moving. And with that single choice you can then predict, with certainty, the matching property of the far cart that your friend is watching across the gym. If you measure position here, you can tell position there. If you measure speed here, you can tell speed there. Nothing you do touches the distant cart. And yet your present choice decides which fact about it you can state confidently, and that gentle strangeness is the doorway to the EPR paradox. The puzzle Einstein, Podolsky, and Rosen framed in 1935. When they asked whether quantum mechanics is complete, they began with two friendly promises about the world, locality, and a modest definition of reality. Starting from those promises, they considered a pair of particles born together in a special way so that their positions and momenta are perfectly linked, while the pair as a whole obeys the quantum rules, and they noticed the same feature as in our carts. By choosing which quantity to measure on particle A, you can infer the corresponding quantity for particle B with certainty. Locality tells you your choice cannot physically disturb B, so by EPR's reality criterion, the property you inferred for B must have been real before you chose. And because you could have chosen the other quantity instead, B must have had both a definite position and a definite momentum at once. But the quantum theory they were testing famously says, you cannot have both quantities sharply defined together, so EPR concluded that the theory must be incomplete, missing hidden details that would restore those definite simultaneous properties. This is not a complaint about randomness for its own sake. It is a carefully stacked argument. If distant influences are forbidden, and whatever can be predicted with certainty without touching is real, then the theory that denies simultaneous sharp values for certain pairs must be leaving something out. Einstein later shaded the mood by calling the implied non-local influence spooky action at a distance. Not to insist on magic, but to underline how uncomfortable it would be to give up locality. Bohr's reply, written in language that reads like a deep breath, did not add new machinery, but questioned EPR's without disturbing clause. In quantum physics, he said, the conditions that make a prediction possible are part of the phenomenon. Choosing a position setup is not a passive peak, but the very context that defines what can be said, while choosing a momentum setup defines a different context, and you cannot mix conclusions drawn from incompatible contexts into one larger statement about what really was simultaneously. There is no single context. free ledger of values hiding behind the scenes. In our cart picture, your ruler, measurement, and your speed. Measurement are not two gentle glances at the same underlying fact. They are alternative games with different scorecards. And the fact that either game lets you predict the far result does not license you to claim both scores for the far cart at once. Frauchiger, watching this debate, gave the shared birth linkage a name, Verscharfeinkung, entanglement, and noticed a sharper trick he called steering. By your choice of what to measure on A, you steer which kind of state you can ascribe to B, even though you never touch B, a surprising but lawful power to set the menu of predictions at a distance, without sending a signal. Because the original EPR setup used position and momentum, quantities fiddly to test with perfect correlations. David Bohm later told a cleaner version using spins that point up or down along any chosen direction. In the singlet pair, the two spins are always opposite along any axis. So the logic becomes simple. You can choose which axis to test on your side, and know what your friend will find along that axis on theirs. And EPR's argument reappears in a form friendly to laboratories. What finally breaks the stalemate is not a metaphor, but a theorem. Bell showed that no model in which each particle carries pre-written answers to all possible questions, and no faster than light nudges occur, can reproduce the full pattern of correlations that quantum theory predicts for these pairs. In other words, if you keep both locality and EPR's style of realism, there's a hard limit to how coordinated the answers can be, and real experiments beat that limit. That does not mean messages fly faster than light, and it does not force you into one single philosophical corner. It does mean EPR's two promises can't both remain untouched. Some researchers relax realism and say properties aren't there with definite values, until a measurement context makes a specific question meaningful. What is real is the relation between system and apparatus. Others relax locality in a careful way, accepting that the joint description of entangled systems is not built from separated, independent parts even when the parts are far apart. While still preserving the no-signaling rule that protects cause and effect, still others keep looking for loopholes in the tests. And modern experiments have gone to great lengths to shut those doors, randomizing the last minute choices with fast physical noise, separating the sites so widely that no light speed signal fits the timing, improving detectors so nearly every event is recorded, even letting starlight set the settings so any hidden coordination would have to stretch back centuries. Through all these refinements, the same core lesson returns like a lullaby played on new strings. The pattern of answers belongs to the pair as a single story, not to two independent stories stitched after the fact. And you cannot assign to each particle in advance a full list of what it would have shown for every possible question that stays compatible with the data, if you also forbid non-local ties. To keep the science crisp and the tone warm for a young listener, distill it like this. EPR asked for completeness, without giving up locality. Quantum mechanics refused by showing that togetherness can run deeper than distance. Bell proved the refusal is not a quirk of math, but a feature the world displays. And experiments heard the world hum the same tune. Newer results add one more layer of understanding without changing the melody. If you treat the quantum state as just a summary of your knowledge, you risk contradicting other theorems that show the state must carry objective weight in how systems can be combined and separated. And if you hope to keep a classical picture by hiding real values underneath, Bell's bound stops you unless you also let influence stretch beyond the naive local frame. What is left is not a demand to believe in ghosts, but an invitation to talk about facts with more care. When a pair is made as one, the safest, most accurate description is joint. When you choose a kind of question here, you define which pattern can be revealed there, not because your choice shoves anything across space, but because the shared recipe only yields certain dishes under matching conditions. And when you feel tempted to ask, what was the other answer the far particle would have given if I had asked a different question here? The kindest reply is that physics does not keep a ledger of unused answers for incompatible questions. The practical harvest is as real as the philosophy is soft-spoken. by exploiting the very correlations that troubled EPR. People now build keys for secret communication that can be certified even if the devices are untrusted. They design networks where entanglement is swapped and extended like a relay race. They test steering inequalities that sit between EPR's original worry and Bell's later proof, showing that one side can demonstrate to the other, without full trust, that entanglement is present. And there is a child-sized wisdom in the middle of all this. Sometimes the world will not let you separate it into parts without losing the point. Sometimes the truth you can tell is a truth about a relation rather than a thing. And learning which kind of truth you're asking for is half the work of understanding. So when you turn the lights down and replay the gym scene in your mind, see the two carts gliding apart on the same smooth track. Feel your choice of ruler or speed gun, and smile at how a question asked tenderly in one place can reveal the shape of an answer far away without ever pushing it there. The universe not as a row of lonely objects, but as a quiet duet where some notes only make sense when heard together. Wave-particle duality, light acting as both. Hold your hand in a sunbeam and watch the tiny dust specks flicker. Then close your eyes and listen to a calm thought. The same light that paints those specks can behave like a smooth, spreading wave, and also like a stream of little clicks that arrive one by one, and whether you meet it as a wave or as a dot depends on the question you ask it. Not because light is a trickster, but because nature lets one thing wear two honest uniforms. Start gently. With waves you already know. When you drop two pebbles in a pond, ripples spread and overlap, sometimes adding to make taller crests, sometimes cancelling to make calm lanes. And light can do this too, bending around edges and making bands of bright and dark in places where straight line bullets could never explain the pattern. You've seen the everyday proof in soap bubbles and oil slicks, where rainbow swirls appear because different colors of light reinforce or cancel at different film thicknesses. And the same happens in a fine comb of closely spaced lines called a grating, which splits white light into a neat spectrum. Those are wave fingerprints, simple and kind. But now turn and meet the other face with steady eyes. If you let light tap a metal plate, it kicks out electrons only when its color is blue enough or violet enough. No matter how faint the lamp, and making the lamp brighter increases how many electrons get kicked, not how energetic each one is. That's the photoelectric effect, and it teaches a child-sized lesson that is quietly deep. Light delivers energy in tiny packets, whose size depends on color. So blue packets are larger than red packets. And you cannot make a red packet do a blue packet's job by piling up many of them in a single, clean punch. When scientists built detectors sensitive enough to hear individual taps, photomultipliers, avalanche photodiodes, the pixels in your phone camera, light began to sound like a rain of single coins. Click, click. Each coin a photon, and that is particle talk as crisp as it gets. The wonder is that neither face is fake. With very faint light, you can let one photon at a time fly toward a setup that would make waves overlap. And you will never see a half-photon smear on the screen, only a lonely dot here or there. Yet if you wait and collect thousands of dots, they build up into the same bright and dark pattern a classical wave would predict, dot by dot arranging themselves where a wave says likely, and avoiding where a wave says unlikely. So a single photon behaves like a particle when it lands, and like a wave when it explores the ways it could go. An answer that is simple to say and slow to feel. Both is not a shrug. It is a rule about how questions shape facts. To keep your mind clear and unafraid, hold three plain truths at once. First, when you ask, where did the light go? By using a detector that waits in a small spot, you force a dot-like answer and get a location. Second, when you ask, how does the light spread? By using screens and slits or films that favor waves, you force a wave-like answer and get fringes and colors. Third, you cannot ask both styles of question at the same time, on the same bit of light, and expect both full answers. The world does not keep a secret ledger of which path that you can consult without dissolving the very interference that needed pathlessness. This is not scolding, it is the architecture of the small. Many bright ideas grew from making peace with that architecture. Max Planck used the packet picture to explain why hot objects glow with a specific color mix. Albert Einstein used it to explain the electron, kicking fact we just met, and later work showed how the packet size and the color are strictly linked. But just as gently, the wavy side of light stayed essential for explaining lenses, radio antennas, and the way light bends as it passes from air into water. So engineers and artists live happily with both faces every day, designing a Wi-Fi antenna as if light is a wave, counting camera photons as if light is a particle, and never getting confused so long as the question is clear. To keep this tale from growing lopsided, notice a quiet echo. If light can act like a particle, matter can act like a wave. Electrons, which you imagine as tiny marbles, can diffract and interfere when guided through fine patterns, and blurry wave packets of atoms have been split and recombined to make exquisitely sensitive sensors, which tells you the duality is not a split personality of light, but a deep rule about how quantum things carry possibilities and deliver outcomes. Yet we promised to keep the focus on light, so return to it with soft curiosity and add one more tool to your belt. Coherence, the idea that waves keep a steady rhythm. A laser is bright, not because it shouts, but because all its photons share a rhythm and phase so well that their waves add cleanly. This is why lasers make sharp spots far away, and why a narrow color makes interference patterns clean, while a messy mix of phases smears the pattern the way a choir out of sync smears a song. When coherence is high, you can see the wave side easily. When it is low, your questions tend to get particle answers. And understanding that lever lets you design experiments like knobs on a radio, tune toward wave, tune toward particle, without any betrayal in the machine. One more gentle puzzle often confuses newcomers. If each photon is indivisible, how can a thin Newton's cradle of glass split a beam into two, as in a beam splitter? The kind answer is that a single photon never becomes half a photon in two places. It takes a wave-like route that has two possibilities and then lands at one detector or the other, with odds set by how the device steers its phase. So the particle nature is preserved at the landing, while the wave nature controls the odds in flight. If you put two splitters and some mirrors together, you can make the odds cancel or reinforce, steering all the clicks to one detector or the other in a way that waves would predict. No half clicks, only full ones, placed by wave logic. A child might ask, can we simply decide once and for all what light really is? And the peaceful answer is this: really belongs to the questions that earn it. In quantum physics, the safest map is to treat the state of light as a complex wave recipe that evolves smoothly when left alone and hands out discrete quanta. When you ask for energy or place, your measurement is the plate you put out, and the dish is served in matching pieces. If that sounds like dodging, remember the test for any idea is whether it helps you build real things. And this one does. Solar panels that harvest photon packets, fiber links that preserve phase so waves can interfere again, microscopes that count single photons to see cells without burning them, cameras that use two light beams whose wave connection beats the blur that would limit any classical design. The dual view is not a poem we keep for comfort. It is a blueprint we use so often it disappears into technology. There is also a friendly boundary to respect. Duality does not mean anything goes. You cannot, for example, use the wave face to smear a message here and have it sharpen there faster than light. The statistics keep causality safe. Nor can you pile many red photons to pop an electron as if they were one blue packet, because energy comes in fixed quanta per photon. The rules are strict and kind at the same time, giving you bold possibilities and clear no's that protect sense. If you want a small handful of pictures to remember, without strain, choose these. Light as ripples on a long rope you shake. Smooth, predictable waves that can add and cancel. Light as a string of marbles hitting a tin roof. Countable, clicky events that carry energy in packets, light as a choreographed crowd, many tiny dancers, whose steps can lock into a common rhythm, or wander randomly, and your instruments as the stage that decides whether you watch them as a flowing pattern or as solo jumps. Each picture is true in its place, and flipping between them is a skill you can practice, not a contradiction you have to fear. In the end, the duality is less a riddle to be solved than a habit of careful asking. Waves whisper how possibilities spread, particles tell you where a result lands, and the art of science is to let both voices speak without talking over each other. So, as you slow your breathing and let the sunbeam on your fingers fade, keep one steady sentence. Light is one thing that answers two kinds of questions with two kinds of truth. And when you learn which question you are really asking, you stop arguing with the sky and start seeing it clearly. Sometimes as a quiet sheet of ripples, sometimes as a sprinkling of sparks, always as the same generous visitor, letting you choose how to listen. The double-slit experiment. Reality splits until you look. Imagine a quiet stage you build yourself. A wide white screen at the back, a little launcher at the front that can toss out the tiniest travelers one at a time, and in between a cardboard fence with two slender doorways, cut side by side so close, you could slide a hair through them, but not a pebble, and you sit there in the hush, like a careful night watchman, letting the launcher fire a single grain, maybe a photon of light, maybe an electron, maybe even a chunkier molecule if you're very patient. And you wait for the soft tick it leaves on the screen. With only the left doorway open, the ticks pile into one gentle hill behind that door. With only the right doorway open, they pile into one gentle hill behind that one. And you nod because that's the world you know. But then you open both at once, and still you send the grains one by one. No crowds, no jostling, and somehow dot after dot after dot, the screen grows a comb of bright bands and quiet gaps, places with many ticks and places with none at all, as if each solitary traveler had explored both doorways and placed its single dot where a larger wave would have said, yes, stand, here, or no, not here. And this is the lullaby, strange heart of the double-slit experiment. Reality behaves as if it splits into multiple routes when you do not ask which route was taken. And it recomposes into a single clear track, the moment your setup is built to care. To keep this simple enough for a child and honest enough for a scientist, say it like this. Before a mark is made, a quantum object is described by a wave recipe that spreads, bends, and overlaps. Two doorways mean two spreading patches of recipe that add together, and the bright bands are where the two patches reinforce, while the dark gaps are where they cancel. So, both ways at once is not a boast but a rule of addition. When at last the traveler hits the screen, the wave recipe does not smudge into a grey haze. It hands you a single dot, a definite place, because screens ask, where, and dots are how. Where is answered. Now lean across the stage with a new idea and attach the tiniest bells to the doorways. Bells so small only one ring would do, or perhaps a microscopic polarizer, or a faint spray of gas that scatters the traveler differently, depending on which door it brushes. And you will notice something soft but firm. The bands fade, the gaps fill, the comb smooths back into two gentle hills. Not because a human eye glared at the doors, not because thought alone changed anything, but because the setup now contains lose that, even in principle, could tell which doorway was used, and once, which way information exists anywhere the two patches of recipe stop adding cleanly. You can even slide your hand along a knob that turns the bells from whisper, quiet to plainly loud, and watch the bands fade gradually, rather than all at once. A physical reminder of a gentle trade-off. The more clearly you make paths distinguishable, the less sharply the pattern of interference can stand, as if your stage can host footprints or ripples, but not both at full strength. No new law is announced when you look. You only choose what kind of question your instruments ask, and the world answers in kind. There is craft in the details that you can learn without numbers. The spacing of the bands depends on the traveler's wavelength and on the doorway's separation, which is why red and blue light paint different ladders, and why a hair's width matters. If you swap light for electrons, you still get bands because electrons have wavelengths, two set by their speed. And if you swap again for large molecules with dozens of atoms, the bands are still there provided your stage is calm enough, and the slits are carved with refined patience. So the lesson is general. Wave recipes belong to matter and light alike. You can see the effect near or far close to the slit. A filigree of self images called a Talbot carpet can appear, while far away the simple ladder sharpens. And you can even play time tricks by opening and closing a single slit in 2 quick bursts, a temporal double slit. That makes bands in energy instead of space, showing that the recipe spreads over when as well as where, and always the same kindness returns. Ask so that alternatives can add, and they will. Ask so that the path is known, and the addition dissolves into either fail. Important myths fall away in this quiet room. The pattern does not require 2 travelers to talk to each other. Run your launcher so dim that minutes pass between ticks and the ladder will still grow. 1 lonely dot at a time. The pattern does not need a person to watch. Leave the room and the bands remain so long as your stage contains no device that could have learned the path, and the pattern is not a scold about certainty. It is a guide to building questions that your equipment can actually answer without stepping on its own toes. If you want to feel how fragile and strong the effect is at once, try this thought experiment. Replace the bells with a single stray photon of light bouncing near a doorway. Even that tiny interaction can carry enough which-way clue to blur the bands. So the art of seeing interference is really the art of keeping the environment from becoming a gossip. Air, molecules, warmth, stray light. Because every unwanted whisper is a half measurement that trades ripples for footprints. This is why good double-slit pictures are made with vacuum pumps humming, shields in place, and cool darkness around the stage. Yet the strength is there in the numbers too, because if you remove the gossips, the bands return exactly where geometry promises, as though the recipe had been waiting politely to sing when the room fell quiet. The experiment also slips you a useful ruler for thinking. If a result is recorded in a way that could be retrieved, if some macroscopic trail or stable correlation exists, then for that run you have asked a path question and lost the interference you might have seen. If no trail exists anywhere, not even in principle, then the world is free to answer with a ladder of bands. And there is neither contradiction nor drama in the difference. A simple life metaphor hides here. Sometimes you learn the most by not demanding a detailed path at every step, because insisting on footprints can erase the delicate pattern you wanted to notice. You can push the stage further and watch how clever arrangements restore or erase path clues deliberately. Attach tiny hats to the travelers at the doors, labels that, by themselves, destroy the bands. And then add a second device that makes the hats irrelevant again before the screen. And the bands reappear when you sort your data by the right key. It looks like undoing the past, but it is really controlling what counts as knowable in the present. And your lesson today keeps the message simpler. Labels that let the world distinguish paths spoil interference. Labels that are made indistinguishable restore it. And in between lies a continuum where partial knowing makes partial bands. All of this lands with a soft philosophical thud that doesn't bruise. The question, what did the particle really do, has no single answer apart from how you set the stage. Because really in the small world is not a claim about a hidden all at-once script, but a statement about measured relations between traveler and doors, between doors and screen, between your choice and the kind of pattern that your apparatus is capable of recording. If that sounds slippery, notice how practical it is. With this one experiment, you can calibrate wavelengths, test the steadiness of a laser, measure slit separations, and even certify that your stage is quiet enough for more delicate tasks, because the ladder's sharpness is a loud report on how much the environment has learned. And as you grow used to the hush, you begin to hear a calm, repeatable truth. Reality is generous with possibilities, but exact about answers. And your kindness as a questioner is to decide which sort of answer you want before you demand it. So let the stage darken again in your mind. the launcher ticking softly, the two doorways standing like thin smiles in the fence, the screen waiting, and you breathing slowly as points appear, and, with patience, weave themselves into bands. Feel how the lesson does not scold you for looking. It invites you to look with intention, to know that asking which way builds a world of footprints, while asking how do possibilities add builds a world of ripples, and that both worlds are honest and lawful, each emerging from the same deep recipe, as soon as you choose the kind of seeing that fits. In that choice lies the simple, sleepy miracle of the double-slit. Nothing supernatural, only one gentle stage, where the many maybes of the tiny become the single dot you can hold, either arranged into a pattern that tells a story of adding, or gathered into hills that tell a story of paths. And in both cases, the universe keeping its promises, while you learn how to ask. Superposition being in two places at once. Start with a picture you haven't held before. Imagine a tiny compass, the size of a dust mote resting on a pin so smooth that the faintest breath could tip it. And instead of choosing north or south, the needle leans into a ghostly angle that is in a precise way. Both leanings at once, like two pencil sketches traced on the same page, so perfectly aligned that only the way the light hits them decides which one your eye will see. That in between leaning is the feeling of superposition, not a coin's secretly heads or tails while you don't know, but a real rule-bound combination of possibilities that behaves differently from any either-or, and we will keep it soft enough for a child, while giving you new tools to carry. Think of each simple quantum choice, left or right, up or down, here or there, as a note you can hum, and a superposition as a chord made from those notes with a particular loudness and a particular timing called phase. And the miracle is not that a thing cheats by hiding. It's that nature allows you to prepare the chord and then use interference to make some futures louder and others quieter before any single note is finally heard, to feel the difference between both at once and I just don't know which. Try this kitchen story. Put a cookie in one of two jars without looking. That is ignorance. And if you shake the table gently, both jars rattle the same way. But if you float a delicate foam bridge between the jars and place the cookie in a true superposition, then a special tap can make ripples from the two sides meet, and either reinforce or cancel on the bridge, changing whether it vibrates at all. Ignorance cannot cancel itself. Superposition can, because what is added or subtracted are wave-like probability amplitudes, not ordinary chances. In the lab, this is more than poetry. Physicists take a single ion and use two quick, carefully timed kicks of microwaves to put its internal magnet into a superposition of up and down. Let it drift like a tiny hand on a clock, whose angle is the phase, and then deliver a second kick that turns the accumulated phase into a yes-no click at a detector. Slide the timing by a hair, and the clicks swing from almost always yes to almost always no. A direct sign that two invisible possibilities traveled together and met, with superconducting loops chilled near absolute zero. Currents can flow clockwise and counterclockwise in a joint state that's neither alone, and the device answers questions in a way that only a superposition could, serving as a qubit, the quantum cousin of a bit that holds the chord 0 and 1, rather than just one note, with beams of very large molecules. Careful physicists send each molecule along paths that recombine and see a pattern appear that would be impossible if the molecule merely took one route, while we remained ignorant. It is the many-atom traveler carried as a single wave recipe and then delivered as a dot. The heart of the recipe is simple to say. Even if the math is shy, a quantum state is a weighted sum of alternatives, and the weights have a direction like the hand of a clock. When two alternatives are brought together, their hands can point the same way, opposite ways, or anything in between. And because the hands spin as systems evolve, you can choose clever timings that make the hand you want line up at the end. This is how atomic clocks tell time with such tenderness that they would lose less than a second over the age of the universe. Each atom is prepared as a superposition of two energy notes that beat against each other, and counting those beats gives a time standard beyond any pendulum. This is also how sensitive sensors reach beyond ordinary noise. Make a superposition that sniffs two slightly different environments at once and recombine it. And the recombined signal carries a phase shift that a single path probe would miss. Faint fields, tiny accelerations, or small rotations leave fingerprints in the angle of that invisible hand. But be gentle. Superposition is not the same as being smeared like butter, nor is it licensed for anything to be anywhere. What can be superposed are the options allowed by the system, and the question you set up. You cannot put a piano and a promise in a chord, but you can put here and there for a neutron, blue and red for a photon, quiet and ringing, for a mechanical paddle small enough to keep its hush. And measurement is not a scolding, but a choice of stage. When you ask, "Where are you?" with a device that can only record a place, the chord is forced to resolve into one note, and you get a dot. When you ask a question that preserves phase, have the hands aligned this way, you hear interference. In between those extremes lies decoherence, the ordinary chatter of the environment, air, warmth, stray light, that steals the phase hand's alignment by carrying away tiny clues about which component of the chord could be read. And when that happens, the power to cancel vanishes and the chord behaves like a plain mixture. This is why superpositions at warm, busy scales are rare, and why quantum computers live in quiet, cold boxes to keep the invisible hands from being jostled before you ask the final question. The cleanest misconception to drop tonight is this: superposition is not a thing is in two places and then chooses one when you look in the fairy tale sense. A truer line is the state is a lawful combination of place answers that predicts how often each place will be found and how different paths will interfere when reunited. In experiments, you can even verify that two components were there together, without asking which was which, by using which component detectors that are deliberately too weak to tell the difference on a single run, but, in aggregate, show the phase tilt growing exactly as a superposition would. This is called weak measurement, and it lets you peek at the turning clock hand without grabbing it. If your mind jumps to "can big things do this?" smile and say, yes, up to the point the world can be kept quiet. Teams are pushing superposition to heavier molecules, to vibrating paddles visible under a microscope, to circuits large enough to draw with a pencil, and each time the challenge is the same. Build a clean chord, protect its phase from the room's gossip, and read it out before the hand's alignment is lost. The reward is practical, as well as philosophical. Better gravimeters to map hidden caves, sharper medical imaging that uses phase to lower dose, navigation that listens to the Earth's rotation in a cloud of cold toms, and algorithms that borrow the many maybes of qubits to cancel wrong answers and amplify right ones in ways classical bits cannot. Here, parallelism is not that the computer checks every answer at once and tells you all of them, but that the amplitudes for many computational paths are carried together, shaped by gates that rotate the hands, and then brought to a final readout where only the patterns that survived interference appear as likely dots. If you want a child's handful of images that have not appeared in our earlier adventures, take these. A lantern placed between two cutout stencils throws overlapping shadows that can brighten or darken where they meet. The lantern is your quantum state. The stencils are the alternatives, and the overlapping darkness is the cancellation that only real superposition makes. A compass whose needle is so small that a whisper can tilt it, and rather than pointing simply north or south, it is prepared pointing northeast. A leaning that is not ignorance, but a deliberate angle that changes under the world's fields, like a slow heartbeat, and a chorus humming two notes that are close in pitch. Stand here, and you hear a swelling and fading called beating. Walk a little, and the pattern changes. Those swells are the phase telling you where interference adds and where it subtracts. The soft closing truth is practical and kind. Superposition is the world's way of keeping possibilities alive, long enough to be shaped by context. And your power as an experimenter or engineer is to choose the context wisely, Ask for phase, and you will get a map of tiny differences with a sensitivity that astonishes. Ask for a place, and you will get a dot you can build with. Ask for both at once, and the apparatus will decide for you, by erasing the very alignment you needed. Learning to live with that trade is not a burden, it is a craft. And it teaches a life lesson too. Sometimes the richest understanding comes from allowing two sketches to coexist until their meeting reveals a pattern you would have missed if you had forced a single outline too soon. So as you slow your breathing, imagine that dust-sized compass again, its tiny needle leaning in a direction that is quietly more than one, and feel how the universe gives you permission to hold maybes gently until the moment you must choose, at which point it answers with a single honest note, just where your question taught it to sing. Schrödinger's cat, dead and alive in a box. Begin with something cozy, not spooky. Imagine a ribboned picnic basket. You're told not to open yet. And inside there's a harmless setup, a little sensor that listens to a shy atom, a latch tied to a party popper, filled with blue confetti, and a sleepy toy kitten wearing a soft bell. The rule is simple. If the atom changes, the sensor tugs the string, the popper blooms, the bell jingles once, and the blanket inside turns a cheerful blue. If the atom doesn't change, nothing happens. No tug, no pop, no jingle, and the blanket stays white. Now pause the scene right after you close the lid and ask the gentle, unnerving question that has kept thinkers awake for decades. Before you peek, is the situation inside best described as either blue or white? But we don't know which, or, because the tiny atom truly allows a superposition of changed and not changed, is the whole basket in a superposed duet, where the atom is both, the sensor is both, the confetti is both popped and unpopped, and the kitten is both sprinkled and not sprinkled all at once. Schrödinger's designed this story to be dissonant on purpose, not to hurt real animals, but to test your habits, because the rule that lets a small thing sit in a carefully prepared Both state is mathematically clean. And when you wire that small thing to macroscopic dominoes, the latch, the popper, the blanket, the jingling bell, the same clean rule says the dominoes themselves should be pulled into the duet. The trouble is that both is not the same as we don't know. And you can tell the difference in principle. Superposition keeps a secret rhythm called phase that can make alternatives reinforce or cancel if you recombine them just right. Whereas ignorance has no phase to cancel. So the cat box puzzle is this. The equations suggest a grand chord of alternatives. Yet our lived world hands us single notes. Do we really live beside boxes that contain chords we never hear? Or is there a moment when chords must turn into notes? And what counts as that moment? To walk forward without heavy math, follow the path of records. Because that's where small maybes become big certainties. If the popper fires, thousands of paper bits stick to fur, millions of air molecules bounce differently. The blanket fibers trap blue specks. The bell's jingle warms the air by a whisper, and each of those little changes is a copy of the outcome. After a heartbeat, the room inside holds a blizzard of copies, and copying like this has a name. Some researchers call it a kind of quantum Darwinism, meaning the world spreads the same fact redundantly, so that many different observers could in principle read it. The practical moral is simple enough for a child. By the time you grab the ribbon, the inside has already chosen a story and shared it with the room, so your eyes don't force a decision so much as they join the chorus. This deflates the scary idea that consciousness makes it happen. No special mind power is needed, because any robust interaction that leaves stable traces counts as a measurement. A camera in the basket would have a picture on its memory card, whether you look or not, and the warm air itself is already a gossip, passing tiny rumors from molecule to molecule, until reversal is beyond hope. But suppose, Schrödinger insists, we imagine a fairy tale basket that leaks no whispers at all. So no air, no stray light, no warmth, no friction, only the tiny atom and the mechanism. And then the clean equations refuse to pick blue or white. Everything stays entangled in one joint, alignment whose halves never talk but also never cancel. A state you could, again in fairy tale principle, recombine and make interfere if you could reverse every step without losing even a single confetti scrap. That impossibly careful recombination is what marks a superposition as different from ignorance. And seeing that difference at large scales is exactly what laboratories chase gently today, with vibrating paddles, levitated beads, superconducting loops, and huge molecules sent along two paths before reuniting them. The bigger the object, the harder the hush, because any bump from the world starts the copying machine, and copying robs you of interference, the way footprints in wet cement rob you of smoothness. What to make of the kitten, then? Both sprinkled and not sprinkled until the lid lifts. There are several calm ways to hold this without repeating old slogans. One way treats the grand chords seriously. The universe keeps both melodies, the blue confetti tail and the white blanket tail. And what turns them into separate worlds is the flood of copies that prevents any future meeting. You will only ever experience one melody because you become part of it. Your hands, your eyes, your notebook join the same chorus, while the other melody continues without you, like two theatre productions that share a script but never share a stage. A second way tweaks the rules of evolution with a tiny extra ingredient that says huge, spread. Outstates are unstable and will randomly snap to one branch with exact odds. This objective fall would happen with no human about, and is being hunted in careful tests that try to make ever larger objects interfere to see whether an unexpected size limit appears. A third way keeps definite stories all along. The kitten is either clean or confetti, kissed in reality, while a wave that fills the basket guides which result shows up with the known statistics. Guidance in that picture reaches in non-local ways, so it keeps the timing of cause and effect safe, yet gives up on the idea that all influences crawl through space point by point. A fourth way changes where you place the word state. It becomes a user's manual relative to an observer. So the kitten relative to the kitten isn't in limbo. Its bell has either rung or not, while you relative to the closed basket must use the balanced manual until a shared record connects you. You do not have to swear loyalty to any one of these tonight to harvest the common lesson they share. Measurement is not about eyes, but about record, making and record. Making is what macroscopic things do constantly. Keep the story child, bright with a different kind of prop. Swap the popper for a color-changing sticker that turns blue when it senses a tiny electric tickle. If the atom flips, the sticker turns blue and emits a faint scent. That faint scent sticks to the cloth. The cloth brushes the wicker warms the air a whisper. These are copies. Make enough copies, and no one can put the scene back the way it was, even if they never look. This is why big living cats never stand in a literal bath, that you could test their breathing, heartbeats, and body heat, write constant diaries on the air. But nothing in that everyday truth forbids small Schrödingers as kittens. We really can make cat-like states of light with opposite phases superposed. Currents in tiny rings flowing both ways. Nanoparticles in two places by a hair's breadth, kept alive in freezers of quiet until we choose a question that reads them out. A few clear takeaways are worth tucking into the basket before you finally peek. Superposition is a structured both, with a phase you can, in principle, test by recombining paths. Ignorance is an either, with no phase to recover. Decoherence is the spread of tiny, uncontrolled copies that erases the chance of recombining. A measurement is any process that makes enough stable copies that many witnesses could agree after the fact. And opening the lid is just one more copy maker, not the start of reality's heartbeat. When you do lift the ribbon in your mind and see either blue confetti or a white blanket, let the closing be soft rather than spooky. The outcome you meet is already woven through the basket, fixed by the records the mechanism and the room have made. The paradox did its kind work by making you name what counts as a fact. And when facts are written, and as you tie the ribbon again, you can carry a steadier way to ask hard questions. Choose your stage so that maybes can sing when you want interference, or so that records are robust when you want a single answer. And know that the point of Schrödinger's cat was never to frighten you with impossible creatures, but to teach you that in a universe generous with possibilities, clarity comes from understanding how and when the little whispers become a chorus. No one can unhear the many worlds puzzle. Every possibility is real somewhere. What if reality were a river that never narrows to a single stream, but forever spreads into a calm delta, each fork as lawful as the next? And your life a small boat that feels only the channel it rides, while countless sister channels slip by out of sight. That is the mood of the many worlds puzzle told gently. Not that imagination invents worlds, but that the standard quantum recipe, one great wave describing everything, evolving smoothly, already contains many mutually exclusive stories. And when measurements entangle you with what you're measuring, those stories peel apart into branches that no longer meet, because the water between them becomes too wide for ripples to cross. In this reading, there is no extra collapse rule that snaps maybes to a single outcome. There is only the one equation humming along, and what we call a world is a stable pattern inside that humming. A self-consistent history where records agree, memories line up, and tables stay solid because decoherence, endless, gentle, jostling with air, light, and heat, locks certain combinations of facts into robust, classical-looking bundles. You can feel the mechanism without math. Think of a coin in superposition as a chord that is partly heads, partly tails. When a detector listens, its atoms become correlated with that chord. Then the room copies the correlation into scattered photons and warm vibrations. Then your eyes and notebook copy it again. Once those copies have spread into the environment, the heads, bundle, and the tails, bundle have different, practically non-overlapping trails through the space of possibilities. So interference between them is lost for all workable purposes. And there is no single ledger left that mixes head facts with tail facts. The bundles go their separate ways like silent canals divided by reeds. It sounds like an explosion of universes, but notice the economy. We didn't add a new law or new stuff. We removed the special, and then it collapses postulate, keeping only the smooth rule and accepting all its consequences. The extra worlds are not new lamps in the attic. They are the ordinary outcomes. The collapse story kept, but then erased, and the price we pay for avoiding erasure is to say they all continue side by side in the big wave, unable to talk after decoherence has pushed them apart. Where then is probability if every outcome happens somewhere? An answer you can carry like a pocket stone is to think in terms of weight and fairness over many trials. The squared size of each branch's chord, the born weight, is like the width of its river channel. Repeat a quantum coin flip 1,000 times, and the bundle of branches where your logbook shows about half heads and half tails occupies almost all the total weight, while the bundle with 90% heads exists, but is thin like a trickle, so rare that a typical observer will never expect to find themselves rowing there. Decision theorists sharpen this feeling by asking how a rational agent should place bets before branching, and they show that if you want your many future versions not to regret your policy, you should act as if the weights were ordinary chances, because policies that ignore them lead to guaranteed worse outcomes for almost all of your successors. There is also self-locating uncertainty in play. Just before you look at the detector, you know there will be multiple U's in near-identical rooms. A moment later, and you can be uncertain which room you will wake up in, even though the global story is fixed. In that short window, caring in proportion to weight matches the frequencies almost every version will later record, turning the abstract rule into the practical odds you already use when you calibrate lasers or time atomic clocks. Common worries can be softened without hand, waving if you keep the river picture clear. Are we multiplying energy each time a branch forms? No. The total energy is a property of the single global wave and stays conserved. while how many worlds is not a counted thing, but a way of grouping nearly non-interfering patterns. A pizza does not get duplicated, the recipe gets split into alternative kitchens that never exchange slices. Are branches science fiction universes with different laws? No. The same law drives all branches, and only outcomes consistent with that law appear. You won't get a branch where momentum stops being conserved or triangles have 4 corners. Could branches meet again? In principle, if you could reverse every microscopic copy the room has made. You could force 2 canals back into one and see interference. Recoherence between stories. But in practice, the copying is spread into absurdly many places. So for cats, people, and notebooks, the canals are separated beyond any bridge we know how to build. While for ions, photons, and tiny circuits, we already do the trick every day. That difference of scale is why your breakfast never blurs, while a superconducting qubit can hum a neat chord. Is the view testable? For lab predictions, it agrees with ordinary quantum mechanics, because both keep the same math for the wave. What it changes is the story we tell ourselves about why only one outcome appears. And if someday someone engineered a controlled interference between 2 truly macroscopic record-laden histories, that would shove us all toward no collapse, while a confirmed size-dependent failure of interference beyond environmental noise would point to a real collapse rule instead. So far, the frontier keeps marching toward larger, colder, quieter systems, and the smooth, only rule has not blinked. Does this picture make choices pointless because some you will do each option, only if you downplay weight and care? The policy you pick now shapes what almost all of your near-future versions will face. Most of the river's water, not a single thin trickle, and that is reason enough to take responsibility. In fact, the many worlds view sharpens responsibility. You cannot hope that a lucky collapse saves you from a reckless bet, because there is no eraser, only a spread of consequences whose sizes you can influence before the forks appear. Where are the worlds located? Not stacked like pancakes in extra space, but distinguished by patterns in the single, high-dimensional wave. Different canals are different directions in possibility, space orthogonal, because decoherence has made them insensitive to each other's ripples. You cannot sail sideways from one to the other, any more than you can turn a melody into a painting by walking across the room. They inhabit the same underlying object, but different coordinates within it. A child, safe metaphor to close the gap between poetry and practice, is a kaleidoscope you do not twist by hand. Inside it, mirrors are replaced by interactions, and every tiny scatter of light sets a slightly different tiling. Once the tilings diverge far enough, no shared shard remains to rebuild the earlier pattern, and each tiling is its own world, to the little figurines drawn on it. Coherent within, deaf to the rest, you are such a figurine, and your instruments are the pieces of colored glass that fix the pattern you inhabit. From here, the technology lesson is simple. Quantum computers do not use all worlds to compute, but they do choreograph amplitudes across many computational paths, and then engineer interference so that wrong answers cancel and right answers add. An art that only makes sense if you respect the reality of the full wave, while accepting that you, at the end, read a single branch's output. Quantum cryptography, metrology, and simulation are similar arts of steering branches and weights without myth. And the soft human closing you ask for? If the river is real beyond your bend, the kindness you can offer yourself is to act as a good ancestor to your most likely successors, to place bets that almost all of your near futures will thank you for, and to let go of the anxious hope for a magical collapse that erases unwise forks. Breathe out and picture the delta stretch, in toward a silver horizon, channels parting, rejoining at tiny scales where we can still coax interference, parting again where life is noisy and warm, and feel how the puzzle is not there to spook you with infinite copies, but to reassure you that the world keeps its law without secret jumps, that your experience is one honest branch among many lawful ones, and that clarity comes from learning how to steer before the water divides. The simulation hypothesis through quantum. Are we just quantum code? Suppose just for tonight, that the universe is a vast nighttime arcade, and you are holding a glowing token. And every star, tree, and fingertip is part of a game so well made that you forget there was ever a screen. That picture is the doorway to the simulation question, told gently through a quantum lens. If reality behaves with rules that are both grainy and graceful, numbers that come in packets, outcomes that land as tiny clicks, could it all be running on some deeper code? And if so, what would that even mean to a child listening under a blanket? Start by translating code into something homier. A recipe, a set of instructions that tells a kitchen when to stir and when to simmer, except this kitchen must serve everything at once, the galaxies and the gnats. And it must do so with perfect timing. Quantum physics hands you clues about how such a recipe would look, not as proof of code, but as constraints any code would have to respect. First, the tiny comes in fixed steps, like the soft tick of a metronome. You can't speed up or slow beyond a limit. So A would be simulator could choose to let space and time be like a hidden grid of fine tiles, or like a flowing fabric that only behaves like tiles when you measure. Either way, the rules must produce the same delicate patterns we see when light and matter are handled carefully. Second, the world's smallest exchanges of energy arrive as indivisible packets, and your detectors count them one by one, which means a code can't smear reality continuously, the way wet paint smears on glass. It must track discrete updates, yet it must also preserve the smooth symmetries that let rockets fly straight and atoms hum steadily. Third, some outcomes are truly unpredictable. Not because we are clumsy, but because the rules themselves allow the future to fork among options with precise odds. So any simulation that uses a simple random seed would have to be generous enough that no clever player inside could distinguish its pseudo dice from the deepest kind of unpredictability we witness. Fourth, distant things can be correlated in ways that no script of pre-written answers could explain, while still refusing to deliver instant messages across the map. So a code that fakes those links would need to choreograph global relationships without breaking the speed limit for usable signals. Like a theater, where two dancers on opposite sides always land together on the downbeat, even though no whispers cross the stage. Thinking this way teaches rather than teases. It tells you what a simulated world must hide well, not that ours is one. If it were code, could we spot the pixels of the game? You might look for a preferred direction in space, a tiniest tick that makes nature slightly lopsided, as if the grid were rotated a little with respect to the stars, or for rounding errors at extreme energies, where the supposed tiles are too big to ignore. You might test whether wild cosmic particles travel exactly the same, no matter how they turn, or whether there is a gentle, universal noise floor that behaves like a quiet housekeeping routine correcting errors in the background. You might even ask whether there's a ceiling on how tangled information can be before the world runs out of memory, the way a small phone struggles with a large video. But here is the calm caution. Every proposed pixel test has at least one ordinary, non-simulation explanation, and careful experiments keep tightening the room in which such pixels could hide without forcing a verdict either way. The same measurements that could reveal a grid also test the symmetries that make modern physics strong, so the hunt is useful whether or not a code exists. The way inspecting a painting for brushstrokes teaches you composition whether or not you find a signature. There is a different brain-tickling angle in which quantum thinking turns the question around. Suppose the basement is not a classical computer pretending to be quantum, but something quantum all the way down, in which case our world is not faked by bits, but ruined by amplitudes, complex numbers that carry both amount and angle like hands of many invisible clocks. So the hidden machine would be less like a row of switches, and more like a chorus of phases, whose harmonies are processed and read out. In that story, what feels like laws of physics are the interpreter rules of an unimaginably efficient quantum engine. And the reason you can't copy certain states perfectly or peak without leaving fingerprints is not because the stage is fragile, but because the interpreter forbids those operations. The way a file format refuses illegal moves you try to make with a half-learned editor. Again, this is not proof. It is a way to keep your thoughts neat. If someone says, "We are code," ask, what kind of interpreter could execute these symmetries and restrictions without falling behind itself? And the quantum answer is one that already knows how to calculate possibilities in parallel and only deliver single outcomes when a question is posed. What would count as a fingerprint of code rather than just of law? Maybe a hard cap on complexity growth that shows up exactly where no known physical limit lies, as if the rendering budget runs out. Maybe a universal checksum pattern, some subtle repeated structure in the background hiss of the universe. That looks exactly like an error, correcting watermark. Maybe a glitchy dependence of results on choices made light, years apart, that still respects the no messaging boundaries, but repeats with a periodicity suspiciously tidy. Or maybe, at the other end, a triumph that corners any classical simulator. If engineers inside the world scale up delicate quantum processors far beyond any classical supercomputer's reach and keep them honest with cross checks only the small world can pass, then any basement trying to fake a quantum universe with classical parts faces a resource bill so tall that either the basement is quantum too or the masquerade will slip. That is a test in spirit, not a practical verdict, but it points to a deep credit. The best way for a universe to look quantum convincingly is simply to be quantum. Two more ideas sparkle here, without promising more than they can give. The first is about storage. The amount of information that can fit in a region seems to scale with the area of its boundary, rather than its volume. A strange bookkeeping that looks like a graceful compression trick. If our world were code, this would be a brilliant space-saving hack. But physics can arrive at the same rule without any programmer in sight, so it's a hint about organization, not a confession of artifice. The second is about protection. Nature often seems to hide important details in ways that look like clever encoding, spreading a delicate recipe across many pieces so that losing a few pieces does not lose the whole. And while that invites you to whisper, "Ah, a designer's redundancy," it also arises naturally when many small parts tug on each other and stable patterns survive. The way a melody survives a missed note because the harmony carries it along. In both cases, the kinder lesson is that information behaves like a physical quantity, with limits and conservation and costs, whether or not anyone wrote it into a game. For a child, you can hold this entire puzzle with a single trustworthy distinction. As if versus is. You can build models that behave as if the world were on a lattice, and compare those models to measurements. You can analyze noise as if it were a housekeeping process, and hunt for it. You can program computers to render physics, and see where they struggle. Each as if gives you a tool, and none of them require the heavier is. Should we live differently if is turned out to be true? The quiet answer is that your reasons for kindness, curiosity, and care survive. Either way, if this is base reality, you owe it respect. If it is a simulation, your choices still shape experiences for minds like yours inside this stage, and meaning belongs to the play as much as to any backstage. Besides, many stories of code smuggle in a trap. If there's a programmer, perhaps you can beg for a miracle or break the rules. But the quantum rules you meet every day leave no back door for special pleading. Only a promise: ask clear questions, get crisp answers, and build better questions next. Code or not, that promise is what makes science the friend it is. So breathe out and let the arcade fade into the night. Imagine the sky not as a ceiling, but as a patient engine of rules that turns possibilities into experiences with perfect timing. Whether some deeper machine hums behind it is a brave question to keep on your desk. But while you keep it, let it guide rather than haunt you. Look for pixels if they help you meta. Sure, listen for housekeeping if it helps you design quieter instruments. Push small devices until their delicacy outpaces every classical pretender. And when you cannot decide between recipe and law, choose the word that keeps you learning. In the end, the softest wisdom this puzzle offers is that wonder doesn't need an author to be real. and that even if we were quantum code, the warmth of holding a hand, the relief of a true explanation, and the hush you feel when the stars switch on would still be exactly what they are now. Honest moments rendered with such care that the only decent response is to notice, to understand a little more each time, and to play kindly in the world we've been given to explore.